Humanity has always sought to understand the origins of the universe, contemplating questions about the beginning of existence. Ancient civilizations often looked to mythologies to explain the cosmos, but as human knowledge advanced, scientific inquiry began to replace these narratives. The question of how the universe began is one that has fascinated scientists and philosophers alike for centuries. With the development of modern cosmology, the most widely accepted theory today is the Big Bang theory, which describes the origin of the universe as an event that occurred approximately 14 billion years ago. The Big Bang theory posits that the universe began from an extremely hot, dense point called a singularity. This singularity contained all the matter and energy that would eventually expand into the universe we observe today. It's important to note that the term Big Bang is somewhat misleading because it suggests an explosion, but in reality, the Big Bang was not an explosion in space. Rather, it was an expansion of space itself. This rapid stretching of space-time occurred at an unimaginable speed, and in the earliest moments, the universe underwent an extraordinary period of inflation. During this inflationary phase, the universe expanded exponentially, growing from subatomic scales to macroscopic scales within a fraction of a second. This expansion wasn't confined to an explosion of material into pre-existing space. Space itself was stretching, and as it did, it carried matter with it. The temperature and density during this early phase were so extreme that no ordinary matter existed in any recognizable form. Instead, there was a sea of elementary particles, quarks, electrons, and neutrinos, bouncing around in a very hot and dense plasma state. These particles would eventually form atoms as the universe cooled down. As the universe expanded and cooled, these particles began to coalesce into the simplest of atoms, hydrogen and helium. Over time, these atoms gathered under the influence of gravity, forming clouds of gas that would eventually collapse to form the first stars. The formation of stars marked the beginning of galaxies as gravity continued to pull matter together, creating vast cosmic structures. The hydrogen and helium atoms in these stars fused together in nuclear reactions, creating heavier elements, which in turn formed new generations of stars and planetary systems. One of the key pieces of evidence supporting the Big Bang theory is the discovery of cosmic microwave background, CMB radiation. In 1965, scientists Arno Penzias and Robert Wilson discovered this faint radiation while working with a radio telescope at Bell Labs. Their discovery was a breakthrough, as the CMB is considered to be the remnant heat left over from the Big Bang. The CMB provides a snapshot of the universe around 380,000 years after the Big Bang, offering a glimpse into a time when the universe was still a hot, dense fog of particles. As the universe cooled, electrons and protons combined to form neutral hydrogen atoms, allowing light to travel freely for the first time. This decoupling of matter and radiation left behind the CMB, which still permeates the entire universe today. The CMB is a critical piece of evidence because it provides a detailed map of the early universe. Scientists can study its properties to learn about the conditions that existed just after the Big Bang. The uniformity of the CMB radiation across the sky suggests that the universe began in a very hot, dense state, and the tiny fluctuations in the radiation allow cosmologists to study the distribution of matter and energy in the early universe. The CMB offers a unique window into the past, enabling scientists to understand the physical processes that shaped the universe. Another important piece of evidence comes from the observation of redshift in the light emitted by distant galaxies. The phenomenon of redshift was first observed by Edwin Hubble in the 1920s. When he measured the light from galaxies, he discovered that the light was shifted toward the red end of the spectrum, indicating that these galaxies were moving away from us. The discovery of redshift was a crucial piece of the puzzle because it showed that the universe was expanding. As light from distant galaxies stretches due to the expansion of space, the wavelength of the light becomes longer, shifting it toward the red end of the spectrum. This observation directly supports the idea that the universe has been expanding since its inception. The concept of the expanding universe, as outlined by the Big Bang theory, provides not only a framework for understanding the universe's origin, but also a critical explanation for the observed abundance of light elements in the cosmos. The period following the Big Bang, especially the first few minutes, was crucial for the formation of the universe's first elements: hydrogen, helium, and trace amounts of lithium. This process, known as Big Bang nucleosynthesis, marks one of the most important steps in the early history of the universe. Understanding how these elements formed and why their relative abundances match current observations offers key insights into the universe's origins and evolution. The theory of Big Bang nucleosynthesis hinges on the premise that the universe was initially in a hot, dense state. Immediately after the Big Bang, the universe was filled with an ultra-hot, nearly homogeneous mixture of particles, including protons, neutrons, and electrons. As the universe began to expand and cool, these particles underwent nuclear reactions that led to the formation of the lightest elements. The process began roughly 3 minutes after the Big Bang, when the temperature of the universe had cooled enough for these nuclear reactions to occur, but was still high enough for atomic nuclei to form. The first and most abundant element to form was hydrogen, which in its simplest form consists of just a single proton. Almost all of the hydrogen in the universe today is thought to have been formed during this early period. As the temperature continued to decrease, protons began to combine with neutrons to form deuterium, a heavy isotope of hydrogen, which then underwent further reactions to form helium-3 and helium-4. These two isotopes of helium are especially important because helium-4, which consists of 2 protons and 2 neutrons, makes up the vast majority of helium in the universe. Small traces of lithium-7 were also formed, though the amount of lithium produced during nucleosynthesis is relatively small compared to hydrogen and helium. The lightest elements, hydrogen and helium, formed so quickly during these first few minutes of the universe's existence that their relative abundances have remained largely unchanged over billions of years. This phenomenon helps to explain why we observe such consistent ratios of these elements across the cosmos today. The isotopic makeup of hydrogen and helium observed in stars, gas clouds, and distant galaxies is in remarkable agreement with the predictions made by the Big Bang nucleosynthesis model. One of the most compelling pieces of evidence for the Big Bang nucleosynthesis model is the observed abundance of hydrogen and helium in the universe. Hydrogen is by far the most abundant element, accounting for about 75% of the visible matter in the universe. This high abundance aligns closely with the predictions made by the Big Bang nucleosynthesis model, which suggests that most of the universe's hydrogen was formed during the first few minutes after the Big Bang. The second most abundant element, helium, accounts for about 25% of the visible matter in the universe. Again, this proportion is strikingly consistent with theoretical predictions, which indicate that helium-4 should make up roughly 25% of the matter in the universe by mass. These proportions provide a direct link between the universe's early conditions and its present state. The fact that hydrogen and helium are so abundantly present in nearly all regions of the universe, from interstellar gas clouds to the cores of stars, strongly supports the idea that these elements were formed in the early stages of the universe's evolution. The agreement between observed and predicted elemental abundances further reinforces the notion that the universe began in a hot, dense state and has been expanding and cooling ever since. While hydrogen and helium are by far the most abundant elements, Big Bang nucleosynthesis also predicted the creation of small amounts of lithium-7. Lithium is much rarer in the universe than hydrogen and helium, and its observed abundance in the universe is somewhat lower than what would have been expected based on nucleosynthesis models. Nonetheless, the relative abundance of lithium in the cosmos is still in close agreement with predictions, and its presence serves as an additional confirmation of the Big Bang nucleosynthesis process. The synthesis of lithium during the Big Bang was significantly less efficient than that of hydrogen and helium, meaning that only trace amounts were produced. These amounts have been preserved throughout cosmic history, contributing to the overall composition of the universe. Interestingly, while the Big Bang nucleosynthesis model accurately accounts for the primordial amounts of hydrogen, helium, and lithium, it is less successful at explaining the formation of heavier elements. Heavier elements, such as carbon, oxygen, and iron, are thought to have been formed later in the interiors of stars through processes such as stellar nucleosynthesis. This is one of the reasons why Big Bang nucleosynthesis is typically referred to as the process that formed the light elements of the universe. The heavier elements that make up planets, stars, and living organisms, on the other hand, were forged through stellar processes that took place long after the Big Bang. The abundance of light elements is not the only evidence supporting the Big Bang nucleosynthesis model. Another critical piece of evidence comes from the cosmic microwave background, CMB radiation, which serves as a snapshot of the universe just 380,000 years after the Big Bang. The CMB provides an imprint of the state of the universe during this early time, when atoms first began to form and the universe became transparent to radiation. The characteristics of the CMB, including its temperature fluctuations and spectrum, offer direct insights into the conditions of the early universe and the processes that led to the formation of the lightest elements. Detailed measurements of the CMB, especially those made by the Planck satellite and WMAP, have provided a wealth of information about the universe's early state. These measurements also confirm the predicted ratios of hydrogen and helium. The uniformity of the CMB across the sky supports the idea that the universe began in a hot, dense state and has been expanding ever since. Furthermore, the precise measurements of the CMB have helped refine our understanding of the exact abundances of hydrogen, helium, and lithium, confirming that these elements were formed during the first few minutes after the Big Bang. The process of nucleosynthesis in the early universe was fundamentally linked to the rate at which the universe expanded and cooled. The key factor in determining which elements could form was the temperature and density of the universe during the first few minutes. As the universe expanded, it cooled rapidly, allowing particles to interact in ways that facilitated the formation of atomic nuclei. However, these reactions could only take place if the temperature was high enough to overcome the repulsive forces between positively charged atomic nuclei, yet low enough for these nuclei to remain stable once they formed. The rate of expansion of the universe had a profound effect on this process. A faster expansion would have cooled the universe too quickly, preventing the formation of certain elements, while a slower expansion might have allowed more elements to form. The observed abundances of hydrogen, helium, and lithium are consistent with the assumption that the universe expanded at a rate that was just right for the synthesis of these light elements. This delicate balance of temperature, density, and expansion rate is what allowed Big Bang nucleosynthesis to proceed in the way that it did, creating the elements that make up the majority of the matter in the universe. While Big Bang nucleosynthesis successfully explains the abundance of light elements, the question of how heavier elements were formed remains a central topic in cosmology. The process that created these heavier elements is not well understood through the Big Bang model. As mentioned earlier, the formation of heavier elements, such as carbon and iron, is thought to have occurred much later in the interiors of stars, through processes like stellar nucleosynthesis and supernova explosions. These processes involve much higher temperatures and pressures than those that existed during the early universe, allowing nuclear reactions to build increasingly heavy atomic nuclei. The study of light element abundances, therefore, plays an essential role in understanding the early universe's chemistry, but it also highlights the limitations of the Big Bang model. While it provides a coherent and robust explanation for the formation of hydrogen, helium, and lithium, it does not extend to the creation of the full spectrum of elements that make up the observable universe. Nevertheless, the model is successful in explaining the distribution of the lightest elements, and it serves as a cornerstone of modern cosmology. The abundance of light elements such as hydrogen, helium, and lithium is one of the key pieces of evidence supporting the Big Bang theory. The process of Big Bang nucleosynthesis, which took place in the first few minutes after the Big Bang, explains why these elements are so abundant in the universe today. The predicted ratios of hydrogen and helium in the universe align remarkably well with current observations, providing strong evidence that the universe originated from a hot, dense state. The study of the light elements, along with the insights provided by the CMB and other observations, continues to deepen our understanding of the universe's origins and the processes that shaped its evolution. The development of the Big Bang theory and the evidence supporting it have fundamentally changed our understanding of the cosmos. The idea that the universe has a beginning and that it has been expanding ever since challenges long-standing notions of an eternal and static universe. It also raises profound questions about the ultimate fate of the universe, as it suggests that the universe could eventually reach a point where its expansion slows down and reverses, leading to a big crunch. Or it could continue expanding indefinitely, cooling and spreading out into an ever more diffuse state. While the Big Bang theory provides the best explanation for the origin and evolution of the universe, it also leaves many unanswered questions. For example, the theory does not explain the exact cause of the Big Bang itself. What caused the singularity to expand in the first place? What happened before the Big Bang? These questions delve into the realms of theoretical physics and cosmology, and researchers are working to understand the fundamental nature of the universe at its most basic level. Ideas such as quantum mechanics, string theory, and the multiverse are being explored as potential ways to answer these questions. The Big Bang theory also faces challenges when it comes to understanding the very early universe. The first few moments of the universe are still shrouded in mystery, as current models break down under the extreme conditions that would have existed during that time. To better understand these early moments, scientists are studying the behavior of quantum fields and looking for ways to reconcile the theory of general relativity with quantum mechanics. Advances in these areas could lead to a more complete picture of the universe's origin and its evolution. As we continue to explore the cosmos, new technologies and methods of observation may reveal even more about the universe's past. The study of the universe's origin is an ongoing journey, one that is deepening our understanding of the fundamental forces that govern the cosmos. In the future, astronomers and physicists may uncover new evidence that will either confirm or challenge the current theories about the Big Bang. Until then, the Big Bang theory remains the most compelling explanation for the origin of the universe, providing a framework for our understanding of the cosmos and our place within it. The study of the early universe is one of the most exciting areas of modern cosmology. The cosmic microwave background, CMB radiation, provides an extraordinary window into the universe's beginnings, offering a snapshot of the cosmos when it was just a few 100,000 years old. The CMB is not merely a remnant from the past. It is a vital tool for understanding the structure, evolution, and fundamental laws of the universe. This faint microwave radiation serves as a cosmic blueprint, revealing temperature fluctuations and the initial conditions of the universe, which in turn provide insights into how galaxies, stars, and other cosmic structures formed. The CMB is the afterglow of the Big Bang, the residual heat left over from the early, hot, and dense state of the universe. Just as light from a distant star carries information about the star's composition, temperature, and age, the CMB carries crucial data about the state of the universe at the time of its formation. It provides us with a snapshot of the universe 380,000 years after the Big Bang, a time when the universe had cooled enough for atoms to form and light to travel freely through space. Before this time, the universe was opaque, filled with a hot, dense plasma of free electrons, protons, and photons, which scattered light in all directions. As the universe expanded and cooled, electrons combined with protons to form hydrogen atoms, and for the first time, photons could travel freely, creating the CMB radiation that we detect today. The CMB is the oldest light we can observe, and studying it is akin to looking back in time to understand the universe's infancy. Its discovery in 1965 by Arno Penzias and Robert Wilson marked a watershed moment in the field of cosmology. Their accidental detection of this faint microwave radiation, which was nearly uniform across the sky, confirmed predictions made by theoretical physicists and cosmologists about the afterglow of the Big Bang. The discovery of the CMB provided strong evidence for the Big Bang theory and established it as the dominant explanation for the origin of the universe. The temperature of the CMB is incredibly low, around 2.725 K, just a few degrees above absolute zero. Despite this low temperature, the CMB carries essential information about the early universe. The uniformity of the CMB across the sky suggests that the universe was once in a hot, dense, and nearly uniform state. However, tiny fluctuations in the temperature of the CMB, known as anisotropies, tell us about the distribution of matter and energy in the universe at the time. These fluctuations are incredibly small, on the order of 1 part in 100,000, but they are key to understanding the processes that led to the formation of galaxies and large-scale cosmic structures. The fluctuations in the CMB are the result of density variations in the early universe. In the first moments after the Big Bang, the universe was dominated by intense radiation and particles. As the universe expanded and cooled, small quantum fluctuations in the density of matter led to variations in the temperature of the CMB. Regions of slightly higher density would have attracted more matter, while regions of lower density would have seen less matter. These small variations would have grown over time, influenced by gravity, to eventually form the galaxies, clusters of galaxies, and other large-scale structures we observe today. The CMB is also important because it allows scientists to measure the age, composition, and expansion history of the universe with remarkable precision. Over the past few decades, instruments like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have mapped the CMB in unprecedented detail. These missions have provided data that has refined our understanding of the universe's properties, such as its age, approximately 13.8 billion years, its overall composition, consisting of about 68% dark energy, 27% dark matter, and 5% ordinary matter, and its rate of expansion. The WMAP mission, which operated from 2001 to 2010, was a major breakthrough in CMB measurements. It provided a full-sky map of the CMB with high resolution and accuracy, allowing scientists to make precise measurements of the universe's parameters. One of WMAP's key contributions was confirming that the universe is flat on large scales, meaning that the geometry of space is consistent with the predictions of inflationary cosmology, a theory that suggests the universe underwent a period of extremely rapid expansion just moments after the Big Bang. The Planck satellite, which operated from 2009 to 2013, further refined our understanding of the CMB. Planck provided even more detailed measurements of the temperature and polarization of the CMB. Its data has helped to measure the Hubble constant, the rate of expansion of the universe, with greater precision, and has confirmed the presence of a mysterious component of the universe, dark energy, that is driving the accelerated expansion of the cosmos. Planck's observations of the CMB have also shed light on the nature of dark matter, a form of matter that does not emit, absorb, or reflect light, making it invisible to telescopes. Although we cannot directly observe dark matter, its presence can be inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. The CMB data provides indirect evidence for the existence of dark matter, and its precise measurements have helped scientists narrow down the properties of dark matter and dark energy, two of the most significant unknowns in modern cosmology. One of the key features of the CMB is its almost perfect blackbody spectrum, which closely matches the theoretical predictions made by cosmologists. A blackbody spectrum is the idealized radiation emitted by a perfect absorber and emitter of radiation, and the CMB's spectrum is remarkably close to this ideal. the near-perfect match between the observed and predicted blackbody spectrum is a powerful confirmation that the universe began in a hot, dense state and has been cooling ever since. The CMB is also polarized, meaning that the light waves oscillate in specific directions. This polarization provides additional information about the early universe, such as the conditions that existed during the first few moments after the Big Bang. The study of CMB polarization can reveal details about the nature of the universe's early expansion, particularly the inflationary period when the universe underwent an exponential expansion in a fraction of a second. Scientists hope to detect the faint signature of gravitational waves in the polarization of the CMB, which could provide direct evidence of inflation and offer insights into the very early universe. The CMB is not just a relic of the past. It is a living tool for cosmologists. By analyzing the CMB, scientists can test different theories about the universe's origin and evolution. For example, by comparing the CMB data with predictions from different cosmological models, scientists can determine which model best fits the observations. The discovery of the CMB has provided answers to many questions, but it has also opened up new avenues for investigation. For instance, the tiny temperature fluctuations in the CMB have led to the discovery that the universe is not only expanding, but its expansion is accelerating, driven by dark energy. The study of the CMB is also crucial for understanding the large-scale structure of the universe. The anisotropies in the CMB provide a blueprint for how matter has clumped together over time, eventually forming galaxies and clusters of galaxies. By studying the CMB, scientists can trace the evolution of these structures from their initial formation to the present day. This has led to the development of cosmological simulations, which model the growth of large-scale structures in the universe and allow scientists to test different theories of galaxy formation and evolution. The CMB also plays a key role in determining the geometry and fate of the universe. The data collected by WMAP and Planck has shown that the universe is flat on large scales, meaning that the total amount of matter and energy in the universe is just the right amount to make space flat. This result has profound implications for the future of the universe. A flat universe will continue to expand forever, but at an ever-decreasing rate. If the universe were open, it would continue to expand indefinitely, but at a slowing rate. If it were closed, the expansion would eventually reverse, leading to a big crunch. In addition to these fundamental questions, the CMB is also helping scientists to answer questions about the ultimate fate of the universe. The study of the CMB is not just about looking back in time, but also about looking forward. By examining the temperature fluctuations and other features of the CMB, scientists can refine their understanding of how the universe will continue to evolve, and whether it will eventually reach a state of equilibrium, continue expanding forever, or collapse back in on itself. The cosmic microwave background radiation is one of the most powerful and essential tools for understanding the universe's origin, structure, and evolution. Its discovery has fundamentally transformed cosmology, providing irrefutable evidence of the universe's hot, dense beginnings. The study of the CMB continues to offer deep insights into the early universe, answering questions about the formation of galaxies, the nature of dark matter and dark energy, and the future of the cosmos. As our observational techniques improve, the CMB will remain a cornerstone of cosmological research, guiding us toward a deeper understanding of the universe in which we live. The realization that the universe is expanding was one of the most profound revelations in the history of modern science. This discovery has reshaped our understanding of the cosmos, challenging long-standing views of a static and unchanging universe. In the early 20th century, the work of astronomer Edwin Hubble fundamentally altered our perspective on the nature of the universe. In the 1920s, Hubble made a groundbreaking observation. Distant galaxies were moving away from us, and the farther away a galaxy was, the faster it appeared to recede. This observation led to the formulation of Hubble's law, which states that the velocity at which a galaxy recedes from an observer is directly proportional to its distance from that observer. This simple but revolutionary idea not only confirmed that the universe was expanding, but also laid the groundwork for the modern understanding of cosmology and the Big Bang theory. Before Hubble's observations, the prevailing view of the universe was largely shaped by the model put forth by Isaac Newton in the 17th century. According to Newton's laws of motion and gravitation, the universe was thought to be eternal and unchanging, with stars and planets in a static, fixed arrangement. The discovery of gravitational forces between celestial bodies, along with Newton's law of universal gravitation, suggested a universe in equilibrium, where everything remained relatively stable. However, this view was not consistent with observations of the cosmos. In the early 1900s, the field of astronomy was undergoing a revolution. The advent of more powerful telescopes, such as the Hooker telescope at Mount Wilson Observatory, enabled astronomers to observe distant galaxies and gather new data about the cosmos. Hubble was instrumental in analyzing the redshifts of light emitted by distant objects, which would become a key piece of evidence in support of the expanding universe. In the 1910s, Vesto Melvin Slipher, an American astronomer, made one of the earliest observations that would later contribute to Hubble's conclusions. Slipher studied the spectra of light from galaxies and noticed that many of them exhibited a redshift, indicating that they were moving away from the Earth. While Slipher's work suggested that some galaxies were receding, it was unclear whether this was a general feature of the universe or just a peculiar characteristic of a few galaxies. Hubble took this research a step further by carefully measuring the distances to galaxies and comparing them with their redshifts. His most significant contribution came in the form of his 1929 paper, where he presented a detailed analysis of the relationship between the distance to a galaxy and its velocity. By using Cepheid variable stars as standard candles to measure distances to galaxies, Hubble was able to determine that the farther a galaxy was from Earth, the faster it was receding. The significance of Hubble's law cannot be overstated. It provided the first empirical evidence that the universe was not static, but rather expanding over time. The discovery that galaxies farther away were receding faster than those closer to us suggested that space itself was stretching, carrying galaxies with it. This observation marked a turning point in the development of cosmology, challenging the long-held belief in a static universe. In the decades that followed Hubble's discovery, the concept of an expanding universe was further developed and refined. Albert Einstein's theory of general relativity, which had been formulated in 1915, played a crucial role in shaping our understanding of cosmology. Einstein's equations described how space and time are interconnected, and how massive objects, such as stars and galaxies, influence the curvature of space-time. In the context of the expanding universe, general relativity provided the theoretical framework to explain the dynamic behavior of the cosmos. Einstein initially introduced a cosmological constant into his equations to allow for a static universe, but after Hubble's discovery of the expansion of the universe, he famously referred to this cosmological constant as his greatest blunder. The realization that the universe was expanding was a direct result of applying general relativity to the large-scale structure of the cosmos. Hubble's law also led to a deeper understanding of the redshift phenomenon. When we observe light from distant galaxies, the light is stretched, shifting toward the red end of the spectrum. This shift occurs because the wavelength of light is stretched as the space through which it travels expands. The redshift of distant galaxies is a direct consequence of the stretching of space itself. In the case of a galaxy moving away from us, the light emitted by the galaxy is stretched as the space between us and the galaxy expands, leading to a redshift. The greater the distance between us and the galaxy, the more space has expanded, and the greater the redshift. The relationship between redshift and distance is a key piece of evidence for the expanding universe. It also provides crucial data for determining the rate of expansion of the universe, known as the Hubble constant. The Hubble constant represents the rate at which the universe is expanding at any given time. By measuring the redshifts of galaxies and their distances, astronomers can estimate the Hubble constant, which has been a subject of ongoing research and refinement. Early estimates of the Hubble constant varied, but more recent measurements have provided a more accurate value. The current best estimate of the Hubble constant is around 70 kilometers (mpc), kilometers per second per megaparsec, meaning that for every megaparsec, approximately 3.26 million light-years, a galaxy is from Earth, it is receding at a rate of 70 kilometers per second. However, there is still some debate in the scientific community about the precise value of the Hubble constant, as different measurement techniques have produced slightly different results. Resolving this discrepancy is an ongoing challenge in cosmology, as it has implications for our understanding of the age and size of the universe. The discovery of the expanding universe had profound implications for our understanding of the cosmos. If galaxies are moving away from us, it follows that at some point in the past, the universe was much smaller and denser. This realization led to the development of the Big Bang theory, which posits that the universe began as a singularity, an infinitely small, hot and dense point, and has been expanding ever since. The evidence of the expanding universe supports this theory and provides a compelling argument for the idea that the universe had a definite beginning. The Big Bang theory suggests that the universe began with a massive release of energy and matter, which triggered the expansion of space. Over time, the universe cooled, and matter began to form galaxies, stars, and other structures. The expansion of the universe continues to this day, with galaxies moving away from each other as space itself continues to stretch. The discovery of the expanding universe, as revealed by Hubble's law, has led to a wealth of scientific discoveries and has shaped our modern understanding of cosmology. One of the most intriguing consequences of the expanding universe is the question of its ultimate fate. If the universe is expanding, will this expansion continue forever? Or will the universe eventually slow down and collapse back in on itself? These questions have fascinated scientists for decades. If the expansion of the universe were to slow down, gravity could eventually cause the universe to collapse in a big crunch. On the other hand, if the expansion continues to accelerate, the universe could expand forever, growing colder and emptier over time. Recent observations, including the discovery of dark energy, suggest that the expansion of the universe is accelerating, which has profound implications for the future of the cosmos. The discovery of the expanding universe also has important implications for our understanding of space-time. According to Einstein's theory of general relativity, space-time is a dynamic and flexible entity that can stretch and warp in response to the presence of matter and energy. The expansion of the universe is a manifestation of this stretching of space-time. This realization has led to new insights into the nature of gravity, the curvature of space-time, and the fundamental forces that govern the universe. The concept of an expanding universe has also led to the development of new theories and models in cosmology. Inflationary theory, which proposes a period of extremely rapid expansion in the very early universe, has gained widespread acceptance. This theory explains many of the observed features of the universe, including the uniformity of the cosmic microwave background, CMB radiation, and the distribution of galaxies. Inflationary theory suggests that the universe expanded exponentially in the first fractions of a second after the Big Bang, smoothing out any irregularities and setting the stage for the development of galaxies and large-scale structures. Hubble's law and the expanding universe have also provided valuable insights into the large-scale structure of the universe. The distribution of galaxies in the cosmos is not random, but rather follows a pattern dictated by the expansion of space. Galaxies tend to cluster together in groups called galaxy clusters, which in turn form larger structures known as superclusters. These structures are connected by vast, empty regions of space known as cosmic voids. By studying the large-scale structure of the universe, cosmologists can learn more about the history of the universe's expansion and the forces that have shaped its development. The discovery of the expanding universe and Hubble's law revolutionized our understanding of the cosmos. Hubble's observations in the 1920s revealed that galaxies were receding from us, and the farther a galaxy was, the faster it appeared to be moving away. This discovery provided the first empirical evidence for the expanding universe and laid the foundation for the Big Bang theory. The study of redshifts, distances, and the Hubble constant has led to a deeper understanding of the universe's history, its rate of expansion, and its ultimate fate. Hubble's law remains a cornerstone of modern cosmology, and its implications continue to shape our understanding of the universe and our place within it. The birth of the universe, as described by the Big Bang theory, was a monumental event that set in motion the processes leading to the formation of the matter we see around us today. In the first few minutes after the Big Bang, the universe underwent rapid cooling and expansion, allowing for the formation of the first primordial elements. The most abundant of these elements, hydrogen, helium, and traces of lithium, were the building blocks for everything that followed, including stars, galaxies, and the complex structures that make up the universe. The process by which these elements formed in the early universe is known as Big Bang nucleosynthesis. This chapter explores the fundamental principles behind Big Bang nucleosynthesis, the predicted abundances of these primordial elements, and the crucial role they played in the development of the cosmos. The Big Bang, which occurred around 13.8 billion years ago, was an event of extreme conditions. In the very early moments of the universe, the temperature was incredibly high and the density was immense. At these extreme temperatures, the universe was filled with a hot, dense mixture of particles, including protons, neutrons, electrons, and various other subatomic particles. This state of the universe is often referred to as the quark-gluon plasma, where quarks and gluons, the fundamental particles that make up protons and neutrons, existed freely, not yet bound into atomic nuclei. As the universe expanded and cooled, the conditions began to change. Around 1 second after the Big Bang, the temperature of the universe dropped enough for quarks to combine and form protons and neutrons. These protons and neutrons would eventually form the nuclei of the first atoms. But before that could happen, the temperature had to decrease even further. Between 3 minutes and 20 minutes after the Big Bang, the universe had cooled enough for nuclear reactions to occur. During this brief period, the process of Big Bang nucleosynthesis took place, resulting in the formation of the universe's first elements. The formation of hydrogen, helium, and lithium during Big Bang nucleosynthesis can be explained by the interplay of fundamental forces and nuclear reactions. Initially, the universe was too hot for atoms to form, as the energetic collisions between particles would have prevented the formation of stable nuclei. However, as the universe expanded and cooled, the conditions became more favorable for nuclear reactions to occur. In the first few minutes after the Big Bang, protons and neutrons began to combine through a process known as nucleosynthesis to form atomic nuclei. The primary products of Big Bang nucleosynthesis were hydrogen, helium, and traces of lithium. Here's how these elements were formed. Hydrogen, the simplest and most abundant element in the universe, was the first element to form after the Big Bang. Hydrogen consists of a single proton, and in the early universe, protons were one of the most common particles. During the first few moments after the Big Bang, the universe was hot and dense enough that protons existed in a plasma state, where they were constantly in motion and interacting with other particles. As the universe expanded and cooled, protons began to combine with electrons to form neutral hydrogen atoms. This process is known as recombination. However, most of the hydrogen formed in the early universe remained in the form of protons and deuterium nuclei, which are isotopes of hydrogen. Deuterium is a stable isotope of hydrogen that contains one proton and one neutron. While hydrogen is the most abundant element in the universe, its formation in the early universe was a complex process influenced by the interactions between protons, neutrons, and photons, light particles. The abundance of hydrogen in the universe today is a direct result of the balance between nuclear reactions and the cooling of the universe during this period. Helium was the second most abundant element formed during Big Bang nucleosynthesis. The process that led to the creation of helium involved the fusion of protons and neutrons to form helium nuclei. This process began when the temperature of the universe dropped enough for protons and neutrons to combine into deuterium. As the temperature continued to decrease, deuterium nuclei began to fuse together, forming helium-3 nuclei, which consist of 2 protons and 1 neutron. These helium-3 nuclei could then fuse with other nuclei to form helium-4, the most stable isotope of helium. The majority of the helium produced in the early universe was in the form of helium-4, which consists of 2 protons and 2 neutrons. The process of helium formation was a key step in the evolution of the universe, as it set the stage for the formation of stars and galaxies, which would later generate heavier elements. Lithium was the third element to form in significant quantities during Big Bang nucleosynthesis, but its production was much more limited compared to hydrogen and helium. The formation of lithium occurred through a series of nuclear reactions involving deuterium and helium-4. These reactions produced small amounts of lithium-7, the most stable isotope of lithium, which consists of 3 protons and 4 neutrons. However, the production of lithium was limited because the conditions in the early universe were not ideal for the synthesis of heavier elements. The temperature and density were not high enough to produce large amounts of lithium, and much of the lithium that was created during Big Bang nucleosynthesis was destroyed in later stages of the universe's evolution. Despite this, the small amount of lithium that remains in the universe today is a key piece of evidence supporting the theory of Big Bang nucleosynthesis. The predictions of Big Bang nucleosynthesis, particularly the relative abundances of hydrogen, helium, and lithium, have been confirmed through a combination of theoretical calculations and observational data. The abundance of hydrogen in the universe is overwhelmingly high, making up about 75% of the normal matter in the cosmos. Helium accounts for about 25% of the matter, with trace amounts of lithium and other light elements making up less than 1% of the total. These predictions match observations of the elemental abundances found in the universe today. For example, observations of distant quasars and gas clouds in the early universe reveal that the amount of helium in these objects is consistent with the predictions made by Big Bang nucleosynthesis models. Similarly, the abundance of lithium observed in the oldest stars and globular clusters matches the predictions of the theory, although there are some discrepancies in the precise amount of lithium found in the universe. These discrepancies are the subject of ongoing research and are an active area of study in cosmology. The relative abundances of hydrogen, helium, and lithium also provide valuable insights into the conditions of the early universe. The fact that the universe contains so much hydrogen and helium and so little lithium is a direct result of the processes that occurred during Big Bang nucleosynthesis. These observations also serve as a test for the lambda cold dark matter (LCDM) model of cosmology, which is the most widely accepted framework for understanding the evolution of the universe. The primordial elements created during Big Bang nucleosynthesis played a crucial role in the formation of stars and galaxies. Hydrogen and helium, the 2 most abundant elements, were the raw materials from which the first stars were formed. In the early universe, regions of slightly higher density began to collapse under the influence of gravity, leading to the formation of protostars. As these protostars continued to collapse, the temperature and pressure in their cores increased, eventually reaching the point where nuclear fusion could occur. The fusion of hydrogen atoms in the cores of these first stars produced helium and released enormous amounts of energy, providing the heat and light that powered the stars. Over time, the fusion of helium and other elements in the cores of stars led to the formation of heavier elements, including carbon, oxygen, neon, and eventually the elements necessary for life. These stars, through their life cycles and eventual deaths, in events such as supernovae, enriched the universe with the heavier elements that would later form planets, life, and the structures we observe today. The formation of galaxies also played a key role in the evolution of the universe. The primordial elements of hydrogen and helium clumped together to form gas clouds, which eventually collapsed under gravity to form galaxies. These galaxies, in turn, became the sites of star formation, and the cycle of star birth, life, and death enriched the cosmos with increasingly complex elements. The early galaxies, composed mainly of hydrogen and helium, were the starting points for the complex structures that would emerge over the next several billion years. Big Bang nucleosynthesis is a cornerstone of modern cosmology. It provides crucial evidence for the Big Bang theory and offers insights into the early conditions of the universe. The theory's predictions about the abundances of primordial elements have been confirmed through a variety of observational techniques, including the study of distant stars, gas clouds, and the cosmic microwave background, CMB radiation. These observations support the idea that the universe began in a hot, dense state and has been expanding and cooling ever since. Big Bang nucleosynthesis also plays a vital role in our understanding of the universe's dark matter and dark energy. The study of the primordial elements and their abundances helps us refine our models of the universe's evolution, providing critical insights into the forces and particles that shape the cosmos. As we continue to observe the universe and make new discoveries, the legacy of Big Bang nucleosynthesis will remain central to our understanding of the cosmos, helping us unlock the mysteries of the universe's earliest moments and its ongoing evolution. The process of Big Bang nucleosynthesis played a vital role in the formation of the primordial elements that shape the universe today. Hydrogen, helium, and traces of lithium were produced in the first few minutes after the Big Bang, setting the stage for the formation of stars, galaxies, and the complex structures that followed. The predictions of Big Bang nucleosynthesis match current observations of the universe's elemental composition, providing strong support for the Big Bang theory and enhancing our understanding of the cosmos. These primordial elements are not just the building blocks of stars and galaxies. They are the key to understanding the universe's evolution and the origins of the matter that makes up everything we observe today. The Big Bang theory, widely accepted as the standard model for the origin and evolution of the universe, offers a compelling framework for understanding the development of the cosmos from its earliest moments. While this theory has been extremely successful in explaining many aspects of the universe's history, such as its expansion, the formation of galaxies, and the cosmic microwave background radiation, it is not without its limitations. These limitations are particularly evident when trying to explain certain fundamental questions that remain unresolved by the theory, such as the nature of the singularity from which the universe originated, the trigger for the Big Bang, and the ongoing asymmetry between matter and antimatter. Furthermore, while the Big Bang theory has made great strides in describing the early universe, it has not been able to fully integrate the principles of quantum mechanics with general relativity, two pillars of modern physics. This chapter explores these limitations in detail and examines some of the theoretical approaches that may address these gaps, such as quantum gravity theories, including string theory. One of the most profound questions raised by the Big Bang theory is the nature of the singularity. At the heart of the theory is the idea that the universe began from a point of infinite density and temperature, known as the cosmological singularity. According to the equations of general relativity, this singularity represents a point in space and time where the curvature of space-time becomes infinite, and the laws of physics as we currently understand them break down. In this framework, the universe's origin is a state of incomprehensible density, where all matter and energy were compressed into an infinitesimally small point. The theory thus implies that time itself began with the Big Bang, and before this event, there was no before in any meaningful sense. However, the very existence of such a singularity raises deep questions about the nature of space and time. The concept of infinite density contradicts our understanding of the physical world. It suggests that the laws of physics, as currently formulated, cease to apply under these extreme conditions. This is one of the significant unresolved issues within the Big Bang theory. It does not explain what caused or even what existed at the singularity before the expansion began. If we are to understand the beginning of the universe, we must develop a theory that can describe the physics of the singularity and what preceded the Big Bang, if anything. The Big Bang theory remains silent on these points, as it only describes the evolution of the universe from a moment after the singularity, not the singularity itself. The inability of the Big Bang theory to explain the nature of the singularity is closely tied to another significant limitation: the lack of an explanation for what triggered the expansion. While the theory effectively describes the evolution of the universe after the Big Bang, it offers no clear understanding of what initiated the expansion in the first place. In other words, the theory does not provide an answer to the question of what caused the initial rapid inflation of the universe, nor why the universe began in such an extremely hot and dense state. The initial expansion is a key aspect of the theory, but it is not explained by the framework itself. This issue is compounded by the fact that inflation theory, which proposes a period of incredibly rapid expansion just after the Big Bang, is itself incomplete. Inflation theory suggests that the universe expanded exponentially during the first fractions of a second after the Big Bang, driven by a mysterious field known as the inflaton field. While this theory explains many features of the universe, such as its large-scale homogeneity and isotropy, it still lacks a clear physical mechanism or explanation for what caused inflation to start. If the universe began from a singularity, what would have caused that singularity to expand at such an extraordinary rate? And what caused the inflationary phase to cease? These questions remain unanswered, and while inflation theory provides a compelling framework, it cannot explain the origin of the expansion itself. Another significant limitation of the Big Bang theory is the issue of the matter-antimatter asymmetry. According to current understanding, the laws of physics should have created equal amounts of matter and antimatter during the early moments of the universe. Matter and antimatter are counterparts, with particles of antimatter possessing opposite charges and quantum properties to those of normal matter. When matter and antimatter come into contact, they annihilate each other in a burst of energy. This process should have led to the complete annihilation of all matter and antimatter in the early universe, leaving behind only energy. However, this is clearly not the case, as the universe is made almost entirely of matter, with antimatter being exceedingly rare. The existence of this matter-antimatter asymmetry is one of the major unsolved problems in cosmology, and the Big Bang theory does not provide a satisfactory explanation for why this imbalance exists. The fact that there is so much more matter than antimatter in the universe remains a mystery. There are various hypotheses that attempt to explain this asymmetry, such as the idea of CP violation of the combined symmetry of charge conjugation and parity in particle physics. This phenomenon could have caused matter to dominate over antimatter in the early universe. However, the amount of CP violation observed in particle physics experiments is not sufficient to account for the observed matter-antimatter asymmetry in the universe. Therefore, this issue remains one of the most significant challenges to the Big Bang theory. Another major limitation of the Big Bang theory is its inability to integrate the principles of quantum mechanics with general relativity. These two fundamental pillars of modern physics describe the universe in very different ways. General relativity, formulated by Albert Einstein in 1915, is the theory that governs the large-scale structure of the universe, describing the behavior of massive objects like stars, planets, and galaxies, as well as the nature of gravity. It explains phenomena like the curvature of space-time and the motion of planets and light. On the other hand, quantum mechanics is the theory that describes the behavior of particles on the smallest scales, such as electrons and photons. It is the foundation of particle physics and describes phenomena like wave-particle duality, quantum superposition, and entanglement. The problem arises when trying to describe the behavior of the universe at extremely small scales, where both quantum effects and relativistic effects are important. The early universe, especially during the Planck era, the first 10 or 43 seconds after the Big Bang, was a realm where both quantum mechanics and general relativity should have played a crucial role. However, the two theories are fundamentally incompatible with each other in this regime, and a complete theory of quantum gravity is needed to reconcile them. The quest for a theory of quantum gravity has led to the development of several candidate theories, the most prominent of which is string theory. String theory posits that the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional strings that vibrate at different frequencies. These strings can explain the behavior of particles and forces at the quantum level, and they also have the potential to unify all of the fundamental forces of nature, including gravity. String theory suggests that the universe has more than the familiar three dimensions of space and one of time, with extra dimensions that are compactified and hidden from direct observation. While string theory holds great promise, it is still a speculative framework, and many of its predictions remain untested. One of the most significant challenges to string theory is that it requires the existence of extra dimensions that cannot be observed with current technology. Additionally, string theory has not yet provided a clear solution to the problem of quantum gravity, and its mathematical formulation remains complex and difficult to test experimentally. Despite these challenges, string theory remains one of the most promising avenues for understanding the nature of the singularity, the cause of the Big Bang, and the integration of quantum mechanics and general relativity. While the Big Bang theory has been remarkably successful in explaining many aspects of the universe's evolution, it faces several significant limitations. These include the inability to explain the nature of the singularity, the trigger for the expansion, and the matter-antimatter asymmetry. Additionally, the theory has not yet reconciled the principles of quantum mechanics with general relativity, leaving many questions about the early universe unanswered. The pursuit of a unified theory, such as string theory, holds promise for addressing these gaps, but much work remains to be done. As our understanding of the universe continues to evolve, it is likely that new theories and discoveries will build upon the Big Bang theory, providing deeper insights into the fundamental nature of the cosmos. While the Big Bang theory remains the prevailing model for the origin and evolution of the universe, it is not the only explanation proposed by scientists over the years. Various alternative theories have emerged, each offering a different perspective on the beginning of the universe, its nature, and its eventual fate. These theories aim to address questions that the Big Bang theory does not fully answer, such as the ultimate origin of the universe, its long-term behavior, and the presence of certain cosmic features. Some of the most significant alternative theories include the steady-state theory, the cyclic universe model, and the epyrotic universe model. Each of these theories challenges the core assumptions of the Big Bang theory and provides unique insights into the cosmos, ranging from the idea of a universe without a beginning or end to the possibility of a universe arising from higher dimensional collisions. While many of these theories have not gained as much traction as the Big Bang theory, they remain valuable in expanding our understanding of cosmic origins and providing alternative models for the universe's past and future. One of the earliest alternative theories to the Big Bang theory is the steady-state theory, proposed by Fred Hoyle, Thomas Gold, and Hermann Bondi in 1948. The steady-state theory presents a fundamentally different view of the universe's origins compared to the Big Bang theory. According to this theory, the universe has no beginning and no end, and it is in a constant state of expansion. Unlike the Big Bang theory, which posits that the universe began from a single point and expanded outward, the steady-state theory suggests that new matter is continuously created in the expanding universe, ensuring that the overall density of the universe remains constant over time. This continuous creation of matter is believed to occur through a process called continuous creation, where new particles are spontaneously formed out of the vacuum of space to replace the matter that moves further apart as the universe expands. In the steady-state model, the universe is eternal, with no specific beginning or end. The expansion of the universe does not lead to a singular origin point, as the universe is always in a state of dynamic equilibrium. This model suggests that the universe is infinite both in space and time, with matter constantly being created as the universe expands, ensuring that the density of matter remains unchanged. The steady-state theory also suggests that galaxies and stars have existed throughout the entire history of the universe, and that their formation and destruction are ongoing processes. One of the main reasons the steady-state theory was proposed was to address the growing realization in the early 20th century that the universe is expanding, as evidenced by the work of Edwin Hubble and others. Hubble's observations of the redshift in the light from distant galaxies suggested that the universe was not static, as had been traditionally believed, but rather expanding over time. The steady-state theory offered an alternative to the idea of a Big Bang by asserting that the universe could continue to expand while still maintaining its overall density through the continuous creation of new matter. However, the steady-state theory faced significant challenges, particularly in light of new observational evidence. One of the most important pieces of evidence against the theory came in 1965, when Arno Penzias and Robert Wilson discovered the cosmic microwave background, CMB, radiation. This radiation, which is a faint glow left over from the hot, dense early universe, provided strong evidence for the Big Bang theory and contradicted the steady-state theory. The existence of the CMB suggested that the universe had undergone a hot and dense phase in its early history, which was not consistent with the idea of a steady-state, eternal universe. Additionally, the steady-state theory struggled to explain the abundance of light elements such as hydrogen and helium, which are predicted by the Big Bang nucleosynthesis models, but cannot be easily accounted for by continuous creation. As a result, the steady-state theory gradually lost favor among scientists, though it remains a part of the historical development of cosmological thought. Another alternative theory to the Big Bang is the cyclic universe model, which proposes that the universe undergoes an endless series of Big Bangs and Big Crunches. According to this model, the universe does not have a single origin point, but instead goes through an infinite cycle of expansion and contraction. The idea of a cyclic universe dates back to ancient philosophy and has been revisited by modern cosmologists in light of new theoretical developments. In the cyclic universe model, each cycle begins with a Big Bang, followed by a period of expansion where the universe grows in size and matter forms into stars, galaxies, and other cosmic structures. Eventually, the expansion slows down, and the universe reaches a point where gravity overcomes the expansion force, causing it to collapse in on itself in a process known as the Big Crunch. After the Big Crunch, a new Big Bang occurs, restarting the cycle and giving rise to a new universe. The cyclic universe model offers a solution to some of the limitations of the Big Bang theory, such as the question of what happened before the Big Bang. In this model, there is no singular beginning. Instead, the universe has existed forever in an endless cycle of birth, death, and rebirth. This concept challenges the idea that the universe had a specific origin point, as proposed by the Big Bang theory. Instead, the cyclic universe suggests that the universe's history is one of perpetual regeneration, with each cycle of expansion and contraction representing a new chapter in the life of the cosmos. One of the most popular versions of the cyclic universe model is based on the idea of string theory and brains, multidimensional objects, from M theory. According to this model, the universe is made up of higher dimensional objects called brains, which exist in a space with more than the familiar 3 dimensions of space and 1 of time. In this model, the universe's cycles are driven by the collision of these brains. Each cycle begins with a collision between 2 brains, leading to a Big Bang-like event, and the universe's expansion occurs as the brains move apart. When the brains eventually collide again, the universe undergoes a Big Crunch, and the cycle repeats. This version of the cyclic universe model provides a possible mechanism for the eternal nature of the universe, offering a way to explain an infinite series of cosmic events without invoking a singular beginning. The cyclic universe model is still highly speculative and faces several challenges. One of the biggest issues is the lack of empirical evidence for the existence of higher dimensional branes, and the idea of brane collisions is still largely theoretical. Additionally, it is unclear how this model can explain the observed uniformity and flatness of the universe, which are predicted by inflation theory, but would be difficult to account for in a cyclic scenario. Despite these challenges, the cyclic universe model remains an intriguing possibility for understanding the ultimate fate of the universe and its possible rebirths. Another alternative theory that challenges the Big Bang theory is the Epyrotic universe, which proposes that our universe emerged from a collision between two higher dimensional branes in a space with more than the usual 4 dimensions, 3 of space and 1 of time. This model draws on ideas from string theory and M theory, suggesting that our universe is not a singular, isolated entity, but rather one of many universes existing in a higher dimensional space. According to the Epyrotic model, the universe we observe today was born from the collision of 2 such branes, which caused the Big Bang-like event that began the expansion of the universe. Unlike the cyclic universe model, which suggests an eternal series of Big Bangs and Big Crunches, the Epyrotic universe model proposes a single, unique event that gave rise to our universe. The Epyrotic model offers a fresh perspective on the origin of the universe, focusing on the dynamics of higher dimensional objects rather than a singular point of origin. The Epyrotic universe theory is also linked to the concept of the multiverse, suggesting that our universe is just one of many that exist in a higher dimensional space. This idea challenges the traditional view of the universe as a single, isolated entity and opens up the possibility of multiple, coexisting universes. The Epyrotic model also offers an explanation for the uniformity and flatness observed in the universe, as it suggests that the collision of branes could have led to a highly uniform distribution of matter and energy across the cosmos. Additionally, the Epyrotic model can potentially resolve some of the fine-tuning issues of the Big Bang theory, such as the problem of the low entropy of the early universe, by suggesting that the conditions of the universe's birth were shaped by the dynamics of brane collisions. Like the cyclic universe model, the Epyrotic theory faces significant challenges in terms of empirical validation. While string theory and the concept of branes are well-developed theoretical frameworks, there is currently no direct evidence for the existence of higher dimensional branes or the collisions that might give rise to a universe. Additionally, the Epyrotic model has been criticized for its lack of testable predictions and its reliance on speculative aspects of string theory. While the Big Bang theory remains the dominant model for the origin and evolution of the universe, alternative theories such as the steady-state theory, the cyclic universe model, and the Epyrotic universe offer intriguing possibilities for understanding the cosmos. These theories challenge the Big Bang theory's assumptions about the origin of the universe and its future, suggesting that the universe may have no beginning or end, may go through infinite cycles of expansion and contraction, or may arise from higher dimensional brane collisions. While many of these theories are speculative and face significant challenges, they expand our understanding of the universe and provide a rich framework for future research. Whether any of these alternative theories will ultimately prove to be correct remains to be seen, but they represent a crucial part of the ongoing scientific exploration of the universe's origins and its ultimate fate. The question of the age of the universe has fascinated humanity for centuries, and answering it has been one of the central goals of modern cosmology. Throughout history, scientists and philosophers have attempted to understand the passage of time and the origins of the cosmos, culminating in the development of increasingly sophisticated methods to measure the universe's age. Over the course of the 20th and 21st centuries, a variety of techniques have been employed to estimate the universe's age, with some methods focusing on the study of cosmic remnants, such as the cosmic microwave background, CMB radiation, the expansion rate of the universe through Hubble's constant, and the ages of the oldest star clusters. Each of these methods provides valuable insights into the universe's timeline, with measurements converging on an estimated age of approximately 13.8 billion years, a figure that has become widely accepted by the scientific community. The cosmic microwave background, CMB, radiation, is one of the most critical pieces of evidence used to measure the age of the universe. The CMB is a faint glow that permeates the entire universe and represents the afterglow of the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB is a remnant of the hot, dense state of the early universe, dating back to about 380,000 years after the Big Bang. The CMB provides a snapshot of the universe at a time when it had cooled enough for atoms to form, allowing photons to travel freely through space. These photons, which were once trapped in the hot, opaque plasma of the early universe, now carry a wealth of information about the conditions that prevailed at that time. The temperature fluctuations in the CMB are crucial for understanding the age of the universe. These fluctuations, which are minuscule variations in the temperature of the radiation, carry information about the density and distribution of matter in the early universe. By studying the pattern of these fluctuations, scientists can extract important cosmological parameters, including the Hubble constant, the density of dark matter, the amount of dark energy, and the overall geometry of the universe. The Planck satellite, launched in 2009 by the European Space Agency, provided the most precise measurements of the CMB to date. Its data allowed scientists to refine their models of the universe's evolution and estimate its age with remarkable accuracy. One of the key results from the Planck mission was the determination of the age of the universe. Based on its analysis of the CMB data, the Planck team calculated that the universe is approximately 13.8 billion years old, with a margin of error of just a few million years. This figure is widely accepted in the scientific community and has become a cornerstone of modern cosmology. The precision of this estimate is the result of decades of advancements in observational techniques, theoretical models, and the development of sophisticated computational tools to simulate the evolution of the universe. While the CMB provides a direct measurement of the universe's age, it is not the only method used to estimate the age of the cosmos. Another crucial technique involves the study of Hubble's constant, which describes the rate at which the universe is expanding. Edwin Hubble in the 1920s discovered that galaxies are moving away from us, and the farther a galaxy is, the faster it recedes. This observation led to the formulation of Hubble's law, which states that the velocity of a galaxy's recession is directly proportional to its distance from Earth. Hubble's constant, denoted as h0, is the proportionality factor in this relationship, and it provides a measure of the expansion rate of the universe. By measuring the recession velocities of galaxies and determining their distances, astronomers can use Hubble's law to estimate the rate of expansion of the universe. This rate of expansion is closely tied to the age of the universe because it determines how long the universe has been expanding. If we know the current rate of expansion, we can reverse the process and calculate when the universe began its expansion, effectively providing an estimate of its age. However, accurately determining Hubble's constant has proven to be a significant challenge, as different methods of measuring it have produced slightly different values. In recent years, there has been a growing tension between two main methods used to measure Hubble's constant. One approach involves measuring the distances to nearby galaxies, using the Cepheid variable stars as standard candles. These stars exhibit a well-known relationship between their luminosity and pulsation period, allowing astronomers to calculate their distances accurately. Using this method, astronomers have estimated Hubble's constant to be around 73 km/mpc. On the other hand, another method involves studying the CMB and its fluctuations, which provides a value of Hubble's constant closer to 67 km/mpc. The discrepancy between these two estimates is a significant puzzle in modern cosmology and suggests that there may be unknown factors influencing the expansion rate of the universe, or it may indicate new physics beyond the standard model of cosmology. Despite this discrepancy, measurements from the CMB, such as those from the Planck satellite, remain crucial for estimating the age of the universe. When combined with other cosmological data, These measurements provide a consistent picture of the universe's evolution, helping to constrain the age of the cosmos. As new techniques and more precise measurements of Hubble's constant become available, scientists hope to resolve the tension between these different estimates and further refine our understanding of the universe's age. Another important method for measuring the age of the universe involves the study of star clusters. Star clusters are groups of stars that formed around the same time and from the same material. By studying the properties of the oldest star clusters, scientists can place constraints on the minimum age of the universe. These star clusters can be divided into two categories: open clusters and globular clusters. Open clusters are relatively young, containing stars that are still in the process of formation, while globular clusters are much older, containing some of the most ancient stars in the universe. The ages of globular clusters are determined by studying the properties of their stars, particularly their stellar evolution. By comparing the observed properties of stars in a globular cluster with theoretical models of stellar evolution, scientists can estimate the cluster's age. The oldest globular clusters are believed to be around 13 billion years old, providing a lower bound on the age of the universe. These estimates are consistent with the age of the universe, derived from the CMB and Hubble's constant, supporting the conclusion that the universe is at least 13.8 billion years old. The study of star clusters also provides important insights into the formation and evolution of galaxies. Star clusters are often found in the halos of galaxies, and their distribution and properties can help scientists understand the processes that led to the formation of galaxies and the cosmos as we know it today. By studying the oldest clusters, astronomers can gain valuable information about the early history of the universe and the conditions that existed during the first few billion years after the Big Bang. In addition to these methods, the age of the universe can also be inferred from the ages of the oldest white dwarf stars and the chemical composition of the universe. White dwarfs are the remnants of low-mass stars that have exhausted their nuclear fuel and are in the final stages of their evolution. By studying the cooling rate of white dwarfs, scientists can estimate their age and thus the minimum age of the universe. These estimates are also consistent with the age of the universe derived from the CMB and star clusters. Measuring the age of the universe has been one of the most important goals of modern cosmology. Over the years, a variety of methods have been developed to estimate the universe's age, including the study of the cosmic microwave background radiation, Hubble's constant, and the ages of star clusters. These methods have converged on an estimate of 13.8 billion years, a figure that has become widely accepted by the scientific community. While challenges remain, such as the discrepancy between different measurements of Hubble's constant, the age of the universe is now known with remarkable precision. Ongoing research in cosmology, astronomy, and astrophysics will continue to refine our understanding of the universe's history and provide even more accurate measurements of its age in the future. The concept of singularities has captivated the imagination of physicists and cosmologists alike for decades. Singularities, at their core, are points where our current understanding of the laws of physics breaks down. These mysterious phenomena, which defy conventional explanation, are central to two of the most profound concepts in modern physics: the Big Bang theory and black holes. Both of these areas offer insight into the nature of singularities, yet they also highlight the limitations of our current models of space, time, and matter. In the context of the Big Bang model, singularities represent the state from which the universe originated. The universe, as we observe it today, began in a singularity, a point of infinite density and temperature where all of space, time, and matter were compressed into an almost incomprehensible small volume. The Big Bang theory suggests that approximately 13.8 billion years ago, the universe began from this singular point, experiencing an explosive expansion that eventually led to the cosmos we know today. The precise nature of this singularity, however, remains one of the greatest unsolved mysteries in cosmology. Current theories of physics, particularly general relativity and quantum mechanics, offer contrasting descriptions of singularities. but both models ultimately break down at these extreme points, suggesting that new physics is needed to explain their true nature. Singularities are places where the mathematical equations used in physics no longer provide meaningful answers. In the case of the Big Bang, the singularity is not a traditional explosion, but rather a state of infinite density and temperature. All matter, energy, space, and time were contained within this point, where the laws of physics as we know them ceased to be applicable. As the universe began its expansion from this singular state, space itself stretched and cooled, allowing particles to form and eventually leading to the formation of atoms, stars, galaxies, and the large-scale structure of the universe. However, the conditions at the moment of the Big Bang singularity remain elusive, as they are beyond the reach of our current observational techniques and theoretical frameworks. Similarly, black holes are associated with singularities, albeit in a very different context. A black hole forms when a massive star collapses under its own gravity, creating a region of space-time where the gravitational pull is so strong that not even light can escape. At the center of a black hole lies a point known as the gravitational singularity, a region of infinite density and curvature where the laws of physics break down. In this context, singularities represent a boundary where our understanding of gravity, space, and time is no longer sufficient. The concept of the black hole singularity was first proposed by Carl Schwarzschild in 1916 as part of his solution to Einstein's general theory of relativity. Since then, the study of black holes has provided important insights into the nature of singularities and the behavior of matter and energy under extreme conditions. The central singularity of a black hole is hidden within the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. Once something crosses this boundary, it is inevitably drawn into the singularity where the known laws of physics cease to operate as they do in the rest of the universe. The nature of the singularity within a black hole is still a subject of intense research and speculation. While general relativity predicts that the singularity is a point of infinite density and curvature, quantum mechanics suggests that quantum effects may prevent such a singularity from forming in the traditional sense. This discrepancy between general relativity and quantum mechanics is one of the primary motivations for the development of theories of quantum gravity, which seek to reconcile these two fundamental theories. The parallels between the Big Bang singularity and black hole singularities have not gone unnoticed by physicists. Both represent states of infinite density and curvature, and both challenge our understanding of space, time, and matter. In both cases, the singularity marks a boundary beyond which the laws of physics as we know them break down, and a new theory is needed to explain the phenomena that occur. The study of black holes has provided valuable insights into the nature of singularities, but much remains unknown. For example, it is still unclear whether singularities truly exist in the way that general relativity predicts, or whether quantum effects might alter their properties. In both cosmological and astrophysical contexts, singularities serve as a reminder of the limits of our knowledge. The Big Bang singularity represents the origin of the universe, but the precise mechanism by which it occurred is still beyond our reach. Similarly, the black hole singularity marks the point of no return for objects that fall into a black hole, but the true nature of this point remains a subject of intense theoretical speculation. While both singularities challenge our current understanding, they also serve as focal points for the development of new ideas and theories. One of the key questions in understanding singularities is whether they represent true physical entities or merely mathematical artifacts of our current theories. General relativity predicts that singularities are regions where the curvature of space-time becomes infinite, but this prediction relies on the assumption that general relativity is the correct description of gravity at all scales. However, general relativity has been shown to break down at extremely small scales, such as those near the Planck length, where quantum effects become significant. As a result, it is possible that singularities do not represent true physical objects, but rather points where our current theories fail to provide accurate descriptions of reality. In recent years, there has been growing interest in the idea that singularities may be replaced by more fundamental structures when quantum gravity is taken into account. String theory, one of the leading candidates for a theory of quantum gravity, suggests that the fabric of space-time is not smooth and continuous, but rather composed of tiny vibrating strings. In this framework, singularities may be replaced by quantum loops or other structures that do not exhibit the infinite density predicted by general relativity. If true, this would have profound implications for our understanding of both the Big Bang and black holes, as it would suggest that singularities are not fundamental features of the universe, but rather artifacts of incomplete theories. Another area of research that may shed light on the nature of singularities is the study of cosmic inflation. Inflation is a theory that proposes that the universe underwent a rapid expansion during the first few moments after the Big Bang, driven by a hypothetical field known as the inflaton field. This period of inflation is believed to have smoothed out the universe and set the stage for the formation of galaxies, stars, and other cosmic structures. Some versions of inflationary theory suggest that the universe could have originated from a quantum fluctuation, rather than from a singularity in the traditional sense. This would imply that the Big Bang was not a singular event, but rather the result of a quantum process that led to the creation of the universe as we know it. The nature of black hole singularities is also the subject of ongoing research in the field of quantum gravity. Quantum gravity is an attempt to merge the principles of quantum mechanics, which governs the behavior of subatomic particles, with general relativity, which describes the behavior of large-scale structures such as stars, galaxies, and black holes. One of the key challenges in quantum gravity is understanding what happens at the singularity inside a black hole, where both quantum effects and gravitational effects are expected to play a significant role. Loop quantum gravity, a leading approach to quantum gravity, suggests that space-time is quantized at the Planck scale, and this quantization may prevent the formation of a true singularity. Instead, the singularity may be replaced by a quantum bounce, where the collapse of matter into a black hole is reversed at a certain point. Despite the progress made in our understanding of singularities, many questions remain unanswered. Are singularities truly points of infinite density, or are they simply the result of incomplete theories? Do black holes harbor singularities, or do quantum effects prevent their formation? Could the Big Bang have originated from a quantum fluctuation rather than a singularity? These questions represent some of the deepest mysteries in modern physics, and their resolution will require new ideas, new technologies, and new ways of thinking about the fundamental nature of the universe. Singularities play a central role in our understanding of both the Big Bang and black holes, yet they also highlight the limitations of our current theories of physics. Whether they represent true physical objects or mathematical artifacts, singularities challenge our understanding of space, time, and matter. As we continue to explore the cosmos and develop new theories of quantum gravity, the study of singularities will remain a crucial area of research, offering the potential for new insights into the very fabric of reality itself. The study of redshift plays a pivotal role in modern cosmology, providing astronomers and physicists with critical insights into the expansion of the universe, the behavior of distant galaxies, and the timeline of cosmic evolution. Redshift refers to the phenomenon where the light emitted by an object is stretched or shifted to longer wavelengths due to the motion of the object away from the observer. This stretching of light is a fundamental tool for measuring the expansion of the universe and for understanding the nature of distant galaxies, stars, and other cosmic phenomena. Redshift is one of the most powerful observational tools available to scientists, enabling them to trace the history of the universe from its earliest moments to its current state. At the most basic level, redshift occurs because of the Doppler effect, which describes the change in the frequency of waves as the source of the waves moves relative to the observer. When an object moves away from an observer, the wavelengths of the light it emits are stretched, causing the light to shift toward the red end of the electromagnetic spectrum. This effect is most commonly associated with sound waves. Think of the change in pitch of a passing ambulance siren, but it applies to all forms of waves, including light. In the case of light, a redshift means that the wavelengths of light emitted by a distant object are stretched to longer, redder wavelengths, making the object appear redder than it would otherwise. Conversely, when an object moves toward the observer, its light is blue shifted, meaning the wavelengths are compressed and shifted toward the blue end of the spectrum. In the context of cosmology, redshift is particularly important because it allows astronomers to measure the recession velocities of galaxies. The most famous observation of redshift came in the 1920s when Edwin Hubble discovered that galaxies were receding from us at speeds proportional to their distance. This observation, now known as Hubble's law, provided strong evidence that the universe is expanding. Hubble's law can be described by the equation V ars 80d, where V is the velocity at which a galaxy is receding, h0 is Hubble's constant, the rate of expansion of the universe, and d is the distance to the galaxy. The redshift observed in the light from galaxies is a direct manifestation of this expansion, as the wavelengths of light emitted by galaxies are stretched as space itself stretches. Redshift is a key tool in measuring the universe's expansion rate, which in turn provides insights into the cosmic timeline. The expansion of the universe has been occurring since the Big Bang, and redshift allows astronomers to track this expansion over time. By measuring the redshift of light from distant galaxies, scientists can determine how far away these galaxies are and, by extension, how long their light has been traveling to reach us. This information is essential for constructing a timeline of the universe's history from its earliest moments to its present state. The relationship between redshift and distance is particularly important because it provides a way to measure the cosmic scale. As light travels through expanding space, it is stretched, which increases its wavelength and causes a redshift. The greater the redshift, the more distant the galaxy, and the further back in time we are observing. In this sense, redshift acts as a kind of cosmic clock, allowing us to look back in time at galaxies as they were in the past. For example, when we observe a galaxy with a high redshift, we are seeing it as it was billions of years ago, in the early stages of the universe. This ability to observe distant galaxies provides a powerful means of probing the early universe, giving us a window into its formation and evolution. One of the most important applications of redshift is its use in studying high redshift galaxies, which are some of the most distant galaxies ever observed. These galaxies, with redshifts typically greater than Z1, provide valuable information about the early stages of the universe. High redshift galaxies are seen as they were when the universe was much younger, often only a few billion years old, and their light has taken billions of years to reach us. By studying these galaxies, astronomers can learn about the processes that led to the formation of galaxies, stars, and other cosmic structures. The study of high redshift galaxies has helped to reveal key aspects of the universe's evolution, including the rate of star formation, the growth of supermassive black holes, and the role of dark matter and dark energy. The study of high redshift galaxies has also revealed important information about the epoch of reionization, a key period in the universe's history that occurred roughly 200 million to 1 billion years after the Big Bang. During this time, the universe transitioned from a neutral state in which atoms were not ionized to a fully ionized state in which atoms were broken up into their constituent protons and electrons. This process of reionization played a critical role in the formation of galaxies and the large-scale structure of the universe. By observing the redshifts of distant galaxies, astronomers can probe the conditions that existed during this epoch and gain insights into the processes that shaped the universe's early history. In addition to providing information about the early universe, redshift also plays a crucial role in the study of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Dark energy is believed to make up about 68% of the total energy content of the universe, yet its exact nature remains one of the biggest unsolved mysteries in cosmology. By measuring the redshift of galaxies at different distances, astronomers can study the rate at which the universe is expanding and how this rate has changed over time. These observations have shown that the expansion of the universe is accelerating, suggesting the presence of dark energy. The study of redshift, in combination with other observational techniques, has helped to establish the existence of dark energy and continues to provide valuable clues about its properties. Redshift is also used to study the large-scale structure of the universe, which refers to the distribution of galaxies, clusters of galaxies, and other cosmic objects on the largest scales. The study of this structure can reveal important information about the cosmic web, a vast network of interconnected galaxy clusters and filaments that make up the large-scale structure of the universe. By measuring the redshift of galaxies in different regions of space, astronomers can map out the distribution of matter and study how it has evolved over time. This information is crucial for understanding the role of dark matter and dark energy in shaping the structure of the universe. To measure redshift, astronomers use a variety of techniques, including the observation of spectra. When light passes through a prism or diffraction grating, it is separated into its component wavelengths, creating a spectrum. The spectrum of light from a galaxy contains characteristic absorption and emission lines that correspond to the wavelengths of light absorbed or emitted by various elements, such as hydrogen, helium, and oxygen. By measuring the displacement of these lines from their expected positions, astronomers can determine the redshift of the galaxy. The greater the displacement of the lines, the greater the redshift, and the more distant the galaxy. The Redshift survey is a major observational effort to measure the redshift of galaxies across the universe. These surveys, such as the Sloan Digital Sky Survey, SDSS, and the 2DF Galaxy Redshift Survey, have provided large datasets that allow astronomers to map the distribution of galaxies and study their properties. These surveys have been instrumental in understanding the large-scale structure of the universe and have provided important constraints on cosmological models. One of the challenges of measuring redshift is the potential for systematic errors, which can arise from factors such as the motion of the observer, the presence of dust in the intergalactic medium, and the influence of gravitational lensing. Gravitational lensing occurs when light from a distant galaxy is bent by the gravitational field of a massive object, such as a galaxy cluster, causing the light to appear distorted or magnified. This effect can complicate the measurement of redshift, as it can alter the apparent position of spectral lines. To mitigate these issues, astronomers employ a variety of techniques, including cross-checking measurements from different telescopes and instruments, and using simulations to model the effects of these factors. In addition to the study of galaxies, redshift is also used to measure the expansion history of the universe through the observation of supernovae. Type Ia supernovae, in particular, are standardizable candles, objects whose intrinsic brightness can be determined with high precision. By measuring the redshift of the light from these supernovae and comparing it to their known intrinsic brightness, astronomers can determine their distance and, in turn, measure the rate of expansion of the universe at different points in time. This technique has been crucial in establishing the accelerating expansion of the universe and has provided key evidence for the existence of dark energy. Redshift is also used to study the intergalactic medium, the diffuse gas that exists between galaxies. The intergalactic medium is primarily composed of hydrogen, which absorbs light at specific wavelengths, creating a distinctive signature in the spectra of distant objects. By measuring the redshift of this absorption, astronomers can study the properties of the intergalactic medium and how it has evolved over time. This information is important for understanding the processes that shape the large-scale structure of the universe and the formation of galaxies. Redshift is one of the most important tools in modern cosmology, allowing astronomers to measure the expansion of the universe, determine the distances to distant galaxies, and probe the early stages of cosmic evolution. Through the study of redshift, scientists have gained valuable insights into the nature of the universe, the expansion of space, the role of dark energy, and the large-scale structure of the cosmos. As observational techniques continue to improve and new instruments such as the James Webb Space Telescope come online, our understanding of redshift and its role in the universe's history will continue to evolve, providing even deeper insights into the mysteries of the cosmos. The origins of the universe, one of the most profound questions in cosmology, continue to spark curiosity and exploration. While traditional models like the Big Bang theory have significantly shaped our understanding, quantum mechanics, a branch of physics that deals with the behavior of particles at extremely small scales, has added a new dimension to these discussions. The interplay between quantum mechanics and the universe's earliest moments offers compelling insights into how the cosmos came into being, how it evolved, and even what might exist beyond our observable universe. The quantum realm's influence on the universe's beginnings is profound, offering a framework in which space-time, energy, and matter were born from fluctuating quantum fields. From the seed of quantum fluctuations, the inflationary period arose, setting the stage for the formation of the cosmos as we know it. In this chapter, we will explore how quantum mechanics influenced the universe's origins, how quantum fluctuations set the stage for inflation, and the possibilities that concepts such as the multiverse present in cosmology today. At the heart of understanding the origins of the universe through quantum mechanics is the idea of quantum fluctuations. These are temporary, spontaneous changes in the energy levels of a point in space, which occur even in a perfect vacuum. In quantum field theory, particles are viewed not as discrete entities, but as excitations of underlying quantum fields. These fluctuations are a natural consequence of the uncertainty principle, a core tenet of quantum mechanics that suggests that there are limits to how precisely we can know certain pairs of physical properties of a particle, such as its position and momentum. In the very early universe, this principle would have governed not just the behavior of subatomic particles, but also the structure of space-time itself. During the Planck era, the first fractions of a second after the Big Bang, quantum fluctuations would have been pervasive, affecting every aspect of the nascent universe. Big Bang was a rapid, exponential expansion of space that would have stretched the universe's size by a factor of 10 to the power 26 in a tiny fraction of a second. This inflationary phase is believed to have been triggered by quantum fluctuations. These fluctuations created the seeds of structure in the universe, influencing the distribution of matter and energy in ways that would later lead to the formation of galaxies and other cosmic structures. Inflationary theory proposes that the universe expanded exponentially, smoothing out any irregularities in spacetime, but preserving the initial quantum fluctuations, which became the density variations that eventually gave rise to the cosmic microwave background radiation, CMB, we observe today. One of the key features of quantum fluctuations in the early universe is their role in creating the initial conditions of the universe. In the standard Big Bang model, the universe begins as a singularity, a point of infinite density and temperature. However, quantum mechanics tells us that such singularities are not physically meaningful. Instead, we must consider the quantum fields and fluctuations that existed before the Big Bang. The notion that quantum fluctuations could have played a role in the birth of the universe is not just a theoretical abstraction, but forms the basis for models such as eternal inflation. In eternal inflation, the rapid expansion of the universe never completely halts. Instead, different regions of space continue to experience inflation at different rates, with the result being an ever-expanding multiverse of diverse bubble-like universes. Eternal inflation suggests that inflation does not occur just once, but rather that it happens continuously in isolated regions of space. Each of these regions becomes a separate bubble universe, expanding rapidly and potentially undergoing different conditions. While one bubble universe may evolve into the universe we observe today, other universes could have very different physical properties, laws of physics, or even dimensions. The concept of eternal inflation challenges our understanding of cosmology, by suggesting that the observable universe is just one small part of a vast, possibly infinite, multiverse. This theory is consistent with certain quantum mechanical models that imply an inherent randomness in the conditions of different universes. The concept of the multiverse arises from quantum mechanics and inflationary theory. In the multiverse model, the universe we observe is not unique. Instead, it is just one of many universes that have emerged from the quantum fluctuations that occurred during the early universe. These universes could have completely different physical laws and constants, leading to entirely different forms of matter, space-time structures, and even different versions of reality. The many worlds interpretation of quantum mechanics, proposed by Hugh Everett in the 1950s, is often cited in discussions of the multiverse. According to this interpretation, every time a quantum measurement occurs, the universe splits into multiple branches, each representing a different outcome of the measurement. If this idea is applied to the universe's origins, it suggests that every possible outcome of quantum fluctuations could give rise to a different universe, leading to the creation of an immense number of universes, all with different properties. Bubble universes are a specific manifestation of the multiverse hypothesis, where each universe is considered a bubble within a larger, eternally inflating space. In this framework, the universe we live in is one of these bubbles that formed during the inflationary period. These bubbles can interact with one another, potentially leading to collisions between universes, although the effects of such collisions remain largely speculative. Some proponents of the multiverse theory argue that bubble collisions might be detectable as anomalies in the cosmic microwave background radiation, offering a potential observational signature of the multiverse. However, these ideas remain controversial, and evidence for the existence of other universes beyond our own is still lacking. The idea of the multiverse introduces a radical departure from traditional cosmological thinking. If the multiverse hypothesis is correct, it suggests that the universe is not just an isolated entity, but part of a larger, more complex system of realities. The implications of such a discovery are profound, challenging our understanding of existence, causality, and the nature of reality itself. For instance, if there are infinite universes with infinite possibilities, the very notion of a fine-tuned universe, one that seems perfectly suited for the existence of life, becomes less remarkable. In the multiverse, the existence of a life-supporting universe might be just one possibility among countless others. This raises philosophical and scientific questions about the role of observation in determining the properties of the universe and the nature of probability in the context of cosmology. Quantum mechanics also plays a crucial role in our understanding of the universe's fundamental laws. One of the central mysteries in modern physics is the lack of a unified theory that can describe both quantum mechanics and general relativity, the theory that describes gravity. These two pillars of physics operate on vastly different scales. Quantum mechanics governs the behavior of particles at the subatomic level, while general relativity explains the behavior of massive objects like stars and galaxies. The quest for a theory of quantum gravity is ongoing, and various approaches, including string theory and loop quantum gravity, aim to reconcile these two frameworks. In these theories, quantum mechanics plays a central role in shaping our understanding of space-time and the fundamental forces of nature. String theory, for instance, proposes that the fundamental building blocks of the universe are not point particles, but rather tiny, vibrating strings. These strings exist in multiple dimensions, some of which may be beyond our perception. In string theory, the quantum fluctuations of these strings could have given rise to the very fabric of space-time, providing an explanation for how the universe emerged from the quantum vacuum. Loop quantum gravity takes a different approach, suggesting that space-time itself is quantized, composed of discrete chunks rather than being continuous. This theory also incorporates quantum mechanics into the description of gravity, offering a possible resolution to the long-standing conflict between general relativity and quantum physics. As we explore the intersection of quantum mechanics and cosmology, we must also consider the philosophical implications of these theories. The notion of an infinite number of universes, each with different physical laws, challenges our traditional ideas of reality and existence. It raises questions about the nature of determinism and free will, the role of observation in shaping the universe, and the concept of fine-tuning, the idea that the conditions of our universe are perfectly suited for the existence of life. If the multiverse exists, the apparent fine-tuning of our universe may simply be a result of the vast number of universes with varying properties, many of which would be inhospitable to life. The relationship between quantum mechanics and the origins of the universe is one of the most fascinating and profound areas of study in modern physics. Quantum fluctuations in the early universe set the stage for the rapid inflationary expansion that followed the Big Bang, shaping the universe's structure and evolution. The possibility of a multiverse, with its endless variations of reality, offers new ways of thinking about the cosmos and our place within it. The challenges of reconciling quantum mechanics with general relativity, along with the quest for a theory of quantum gravity, will continue to drive research in cosmology and fundamental physics for years to come. As we deepen our understanding of the quantum nature of the universe, we may uncover even more profound insights into the origins of everything we know. The mysteries of the universe's origins have long been a subject of deep intrigue for cosmologists and physicists alike. One of the most fascinating and groundbreaking ideas that has emerged in the past few decades is that of eternal inflation, a theoretical framework that posits the continual creation of new bubble universes from an underlying inflating space. This concept, along with the related theory of chaotic inflation, provides profound explanations for the observed fine-tuning of our universe and the incredible diversity of cosmic conditions observed across the universe. These theories challenge our understanding of reality, presenting the possibility that our observable universe is just one of an infinite number of universes that exist within an ever-expanding multiverse. Eternal inflation is an extension of the inflationary model of the early universe, a theory proposed by physicist Alan Guth in 1980. The basic idea behind inflation is that in the first fractions of a second after the Big Bang, the universe expanded exponentially at an incredibly fast rate. This expansion stretched space-time by a factor of 10^26 in a mere 10^36 to 10^32 seconds, smoothing out the distribution of matter and energy and solving several key problems in the standard Big Bang model, such as the horizon problem and the flatness problem. However, inflationary theory alone did not account for the nature of the universe we observe today, leading to the development of eternal inflation, which offers a more profound explanation of the cosmos's origins. Eternal inflation suggests that inflation does not stop after the initial burst of expansion, but continues in certain regions of space. This perpetual inflation causes different parts of spacetime to expand at different rates, resulting in the formation of isolated bubble universes. These bubble universes are self-contained, with their own laws of physics, constants and properties, but they all emerge from the same inflationary process. The term eternal refers to the idea that inflation is an ongoing process, one that continually generates new bubbles and potentially new universes. The key feature of eternal inflation is that different regions of spacetime experience inflation at different rates, leading to a never-ending process of universe creation. In this framework, while inflation might slow down or stop in some regions, it continues indefinitely in others. Over time, the universe becomes a vast, ever-expanding multiverse of bubble universes, each one potentially differing in its physical laws and constants. This multiverse model provides a radical departure from traditional cosmological thinking, suggesting that the observable universe is just one part of an infinitely larger reality. In addition to eternal inflation, another important variant of inflationary theory is chaotic inflation, which was introduced by Andre Linde in the 1980s. Chaotic inflation is a more specific version of inflationary theory that proposes the universe began in a highly energetic, chaotic state. Unlike the more structured view of inflation, where a smooth field drives the rapid expansion, chaotic inflation suggests that inflation arises from a random, disordered state in which quantum fluctuations play a central role. These fluctuations lead to the formation of local regions of space where inflation occurs, resulting in the creation of distinct bubble universes. The fundamental idea behind chaotic inflation is that the energy density of space was initially very high, and quantum fluctuations during this period caused some regions to become unstable, leading them to experience rapid inflation. The regions that undergo inflation expand exponentially, eventually decoupling from the original high-energy environment and forming independent bubble universes. These universes are characterized by their own set of physical laws and constants, which may differ dramatically from one another. One of the key aspects of chaotic inflation is its ability to explain the fine-tuning problem. The observation that the constants of nature and the conditions of our universe seem perfectly tailored to allow life to exist. In the chaotic inflation model, the idea of many universes emerging from the same inflationary process suggests that the apparent fine-tuning of our universe might be nothing more than a statistical outcome of the vast number of universes in the multiverse. In this view, it is not surprising that at least one of these universes, such as ours, is capable of supporting life. The universe we observe could be one of the many random outcomes of chaotic inflation, where the conditions that allow life to thrive simply happen to emerge in one of the countless bubble universes. One of the most striking aspects of both eternal and chaotic inflationary theories is their ability to provide a natural explanation for the fine-tuning of the universe. Fine-tuning refers to the precise values of the fundamental constants of nature, such as the strength of gravity, the charge of the electron, and the cosmological constant, that seem to be perfectly balanced to allow the existence of life. Small changes in any of these constants would render the universe inhospitable to life as we know it, leading many to wonder why the universe is so finely tuned. The multiverse models proposed by eternal and chaotic inflation offer an elegant solution to this problem. In these models, the fine-tuning is not a miraculous coincidence, but rather a statistical outcome. With an infinite number of universes, it is not surprising that at least one would have the right conditions for life. In the context of chaotic inflation, the chaotic, random nature of the inflationary process ensures that there is a vast diversity of possible outcomes, each with different values for the fundamental constants. Some universes will have conditions suitable for life, while others will not. This statistical reasoning alleviates the need for an external explanation for why our universe has the right conditions for life. Such conditions are simply one possibility among an infinite number of outcomes. Moreover, the theory of eternal inflation further strengthens the idea of a fine-tuned multiverse. Since inflation is a continuous and eternal process, the number of bubble universes generated over time becomes infinite. This provides an even more compelling argument for the likelihood of fine-tuning occurring by chance. In this sense, eternal inflation offers a framework in which our universe is just one among an infinite number of universes, each with different physical properties, laws, and constants. The multiverse thus provides a natural explanation for why our universe appears to be finely tuned for life. It is simply one of the many universes that arose from the inflationary process. And it just so happens to be one where the conditions are right for life to emerge. Despite its many appealing features, the theory of eternal and chaotic inflation is not without its challenges and controversies. One of the primary criticisms of these theories is the lack of direct observational evidence. While the predictions of inflationary models, such as the cosmic microwave background radiation, CMB, have been supported by observations, the idea of a multiverse and the continual creation of bubble universes remains speculative. Theoretical models suggest that bubble universes may not be detectable by our current instruments, and therefore, testing the existence of the multiverse is a significant challenge. Moreover, the scientific falsifiability of eternal and chaotic inflation has been questioned. In science, for a theory to be considered valid, it must be testable and falsifiable through empirical observation and experimentation. However, the multiverse theories proposed by eternal and chaotic inflation seem to lack this property. If each bubble universe is causally disconnected from the others, then it is unlikely that we will ever be able to observe or interact with other universes in the multiverse. This raises philosophical questions about the nature of scientific theories and whether concepts that cannot be tested or observed are meaningful within the framework of empirical science. Additionally, the concept of eternal inflation raises questions about the nature of time and the initial conditions of the universe. If inflation is eternal, does it imply that time itself is infinite, or does it mean that the universe undergoes an infinite series of beginnings and endings? These are deep metaphysical questions that are not easily resolved within the framework of current cosmological models. Despite these challenges, the theories of eternal and chaotic inflation have opened up new avenues for understanding the origins and structure of the universe. As we continue to explore the implications of the multiverse and the role of inflation in shaping the cosmos, we may uncover more insights into the fundamental nature of reality. The discovery of gravitational waves, for example, could provide new information about the early universe and the inflationary period. Future advancements in observational cosmology, particularly through increasingly powerful telescopes and space missions, could also provide indirect evidence for the existence of a multiverse or bubble universes. In the long run, the study of eternal and chaotic inflation may lead to a deeper understanding of the very nature of existence itself. By exploring the possibility of a multiverse, we challenge the very notion of a single, unique universe and open the door to the idea that reality, as we know it, could be part of an infinite and ever-expanding cosmic landscape. The theories of eternal and chaotic inflation not only reshape our understanding of the universe's origins, but also invite us to reconsider the very nature of reality, time, and existence in the cosmos. The theories of eternal inflation and chaotic inflation represent a radical and exciting evolution in our understanding of the universe's origins. By suggesting that the universe is part of a vast, ever-expanding multiverse, these theories provide explanations for the fine-tuning of the cosmos and the diversity of physical conditions observed in the universe. While challenges remain in testing these theories and proving the existence of a multiverse, the implications of these models are profound, reshaping our view of reality and the very fabric of the cosmos. As we continue to explore the origins of the universe, eternal and chaotic inflation may play a key role in unlocking some of the deepest mysteries of existence. The multiverse concept is a profound and revolutionary idea that challenges many long-standing assumptions about the nature of our existence, the universe, and reality itself. It posits that our observable universe, with all its galaxies, stars, and planets, is just one of potentially countless other universes that exist beyond our perception, each with its own set of physical laws, constants, and properties. The idea that there could be other universes, each with different characteristics, raises fundamental questions about existence, the fabric of reality, and the very nature of the cosmos. The multiverse hypothesis is not a new concept. It has roots in both ancient philosophy and modern theoretical physics. For centuries, philosophers and cosmologists have speculated about the possibility of other worlds with varying degrees of acceptance and understanding. However, it was only in the 20th and 21st centuries that scientific theories, particularly those involving quantum mechanics, string theory, and eternal inflation, began to provide frameworks in which the multiverse could be studied and understood. These theories have introduced new ways of thinking about the universe, suggesting that our universe may be part of a much larger and more complex cosmic structure. One of the key drivers of the multiverse concept is the idea that the universe we observe is highly fine-tuned for life. The constants of nature, such as the strength of gravity, the mass of elementary particles, and the properties of forces like electromagnetism, appear to be precisely calibrated to allow the existence of complex structures like stars, planets, and ultimately, life itself. This fine-tuning problem has puzzled scientists for years. If the values of these constants were even slightly different, life as we know it would not be possible. Some physicists have suggested that the multiverse could provide a natural explanation for this fine-tuning. In a multiverse scenario, there would be an infinite number of universes, each with different values for the fundamental constants. It would not be surprising that one of these universes, our own, happened to have the right conditions for life. The concept of the multiverse has gained considerable support from several leading theories in theoretical physics. One of the most prominent of these is string theory, which attempts to unify all of the fundamental forces of nature, including gravity, into a single, consistent framework. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can exist in higher dimensions beyond the familiar 3 dimensions of space and 1 dimension of time that we experience in our daily lives. In string theory, the idea of the multiverse arises naturally. The theory proposes that there could be many different ways in which the extra dimensions of space can be compactified, leading to different types of universes with varying physical properties. Each solution to the equations of string theory could correspond to a different universe with its own distinct laws of physics. Another key theory that supports the multiverse is the idea of eternal inflation. This concept builds upon the standard inflationary model of the early universe, which suggests that the universe underwent a rapid period of exponential expansion in the first moments after the Big Bang. Eternal inflation extends this idea, proposing that inflation is an ongoing process that occurs in different regions of space. In this model, certain regions of space undergo a process of rapid inflation, while other regions stop inflating and give rise to what we observe as the universe. However, inflation continues in other regions, leading to the creation of bubble universes. These bubble universes, which could have different physical properties and constants, would be isolated from one another and unable to interact. The eternal inflation model thus suggests that our universe is just one of countless others that are continuously being created in an ever-expanding multiverse. Quantum mechanics, the fundamental theory that governs the behavior of particles on the smallest scales, also provides support for the multiverse concept. In particular, the idea of quantum fluctuations and the many worlds interpretation of quantum mechanics suggests that every possible outcome of a quantum event actually occurs, but in different branches of reality. According to the many worlds interpretation, every time a quantum event happens, such as the measurement of a particle's position or momentum, the universe splits into multiple versions, with each version corresponding to a different outcome of the event. This branching process continues indefinitely, creating an ever-growing number of parallel universes. These universes are not just theoretical. In the many worlds interpretation, they are real and tangible, each representing a different version of reality. While these theories suggest the possibility of a multiverse, they also raise a host of philosophical and scientific questions. One of the most profound questions is whether the multiverse is a scientifically valid concept at all. For a theory to be considered scientific, it must be testable and falsifiable. However, the multiverse hypothesis presents a challenge to these criteria. Since the different universes in a multiverse are, by definition, causally disconnected from each other, it may be impossible to gather direct observational evidence of their existence. Some critics argue that because the multiverse theory cannot be tested or falsified, it is not a legitimate scientific theory. Others contend that the very nature of a multiverse means that it may not be accessible to our observational techniques, but this does not necessarily invalidate the idea. Another significant philosophical issue raised by the multiverse concept is the question of existence and reality. If there are infinite universes, each with different properties, what does that mean for the nature of our own universe? Are we merely one random outcome among many, with no special significance? Some have argued that the multiverse undermines the idea of a unique, meaningful existence. If there are an infinite number of universes, Does anything really matter? In this view, the existence of the multiverse could be seen as an existential threat to our understanding of purpose and meaning. However, others argue that the existence of many universes could actually enrich our understanding of reality, offering new possibilities and insights into the fundamental nature of the cosmos. Furthermore, the idea of the multiverse raises important epistemological questions about what we can know and how we know it. If our universe is just one of countless others, how can we ever be sure of what is true about the universe? The multiverse challenges the idea that there is a single objective reality that we can observe and understand. Instead, it suggests that our perceptions of the universe may be limited by the specific laws and constants that govern our own bubble universe. This leads to a deeper question about the limits of human knowledge and the scope of scientific inquiry. Are we capable of understanding the full nature of reality, or are we confined to a tiny corner of the multiverse, with our knowledge and understanding forever limited by the boundaries of our own universe? In addition to these philosophical challenges, the multiverse theory has implications for other areas of scientific inquiry. For example, the discovery of the cosmic microwave background radiation, CMB, and the study of large-scale cosmic structures have provided strong evidence for the Big Bang model of the universe. However, if the multiverse exists, does this mean that the Big Bang is just one event in an infinite series of cosmic events? Could the CMB be evidence of our universe's place in a much larger multiverse? These are questions that remain unanswered, and the answers may not come easily. As our understanding of the multiverse continues to evolve, new tools and methods will be needed to explore these deep and complex issues. The implications of the multiverse concept are far-reaching, not just for cosmology, but for our understanding of existence itself. The existence of multiple universes could fundamentally alter our perspective on the nature of life, the universe, and everything in it. It could provide a natural explanation for many of the mysteries of the cosmos, from the fine-tuning of physical constants to the origins of life itself. It could also offer new insights into the very structure of reality, suggesting that the universe we observe is just one piece of a much larger and more intricate cosmic puzzle. The concept of the multiverse challenges many of our deepest assumptions about the universe and reality. Supported by theories such as string theory, eternal inflation, and quantum mechanics, the multiverse suggests that our universe is just one of countless others, each with its own unique properties and characteristics. While the idea of the multiverse raises profound philosophical and scientific questions, it also offers exciting new possibilities for understanding the nature of existence. As our knowledge of cosmology continues to advance, the multiverse concept may provide the key to unlocking some of the most profound mysteries of the cosmos. Whether the multiverse is ultimately proven to exist or not, its exploration will continue to shape our understanding of the universe and our place within it. The fine-tuning of the universe is a remarkable and profound concept in modern cosmology, referring to the precise calibration of various physical constants and conditions that make the existence of life possible. These constants include fundamental aspects like the strength of gravity, the electromagnetic force, and the masses of elementary particles. Each of these factors appears to be finely tuned to a degree that seems improbable, and it raises the question of why the universe operates in such a finely balanced way. The fine-tuning argument suggests that even the slightest variation in any of these constants would render the universe incapable of supporting life, or in some cases, incapable of existing at all. This delicate balance has sparked much debate among scientists, philosophers, and theologians, with different interpretations of what it implies about the nature of the cosmos, the possibility of other universes, and the role of life in the universe's vast expanse. The precise calibration of the physical constants is often illustrated by examples from various aspects of nature. One of the most well-known examples is the force of gravity. If the gravitational constant were even slightly weaker, stars would not have enough mass to initiate nuclear fusion, which is responsible for their energy production. Stars are the primary source of light and heat for planets, and without them, complex structures like planets and life forms would never emerge. On the other hand, if gravity were stronger, stars would burn out too quickly, again preventing life from developing. These examples of gravity's delicate balance in nature are just the tip of the iceberg. The strengths of the fundamental forces in nature, such as the strong nuclear force and the weak nuclear force, must also fall within narrow ranges to allow for the formation of atoms, molecules, and eventually, life itself. Another crucial constant is the electromagnetic force, which governs the behavior of charged particles. The strength of the electromagnetic force determines the size of atoms and the nature of chemical bonding. A slight change in this force would prevent the formation of stable atoms or make chemical reactions impossible, thus eliminating the possibility of complex molecules like DNA, proteins, or even simple molecules required for life. These examples highlight the seemingly improbable precision required for life to exist. Moreover, the fine-tuning extends to conditions like the cosmological constant, which dictates the expansion rate of the universe. If this constant were too large, the universe would have expanded too rapidly after the Big Bang for galaxies and stars to form. If it were too small, the universe would have collapsed back on itself, preventing the formation of the large-scale structure we observe today. The apparent fine-tuning of this constant is a major area of research and debate, particularly in the context of dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. One of the most striking aspects of the fine-tuning argument is the improbability of these constants being so precisely calibrated for life. The idea that these constants could have any values other than those that allow life as we know it seems counterintuitive. If the constants were determined by chance alone, it seems exceedingly unlikely that they would align in such a way as to permit the emergence of life. For this reason, some have argued that the universe's fine-tuning points to the possibility of a designer or creator who deliberately set the conditions for life to exist. This interpretation has been the subject of much philosophical and theological debate, with proponents of intelligent design suggesting that the precision of these constants could not be the result of mere chance. In contrast to this view, many scientists suggest that the fine-tuning of the universe could be explained by the anthropic principle, a concept that has gained traction in cosmology and philosophy. The anthropic principle proposes that the universe must have the properties necessary for life, because if it did not, life would not be here to observe it. In other words, the universe is fine-tuned for life simply because if it weren't, there would be no conscious beings to ponder such a question. According to this principle, the fact that we observe a universe that appears to be finely tuned is not surprising, because if it weren't, we wouldn't be around to ask why it is fine-tuned. The anthropic principle can be divided into two main forms: the weak anthropic principle and the strong anthropic principle. The weak version simply suggests that the physical constants of the universe are such that life can exist, and we are here to observe it because we live in a universe that is conducive to life. The strong version, on the other hand, implies that the universe is somehow compelled to have the properties necessary for life, perhaps through a more purposeful or deterministic process. In addition to the anthropic principle, the fine-tuning of the universe is sometimes used as evidence for the existence of a multiverse. The multiverse hypothesis suggests that our universe is just one of many, each with its own set of physical laws and constants. If there are an infinite number of universes, it would not be surprising that at least one of them, our own, has the conditions necessary for life. In this context, the fine-tuning of our universe could be seen as a natural consequence of the larger multiverse, where the vast majority of universes are inhospitable to life, but a few, like ours, just happen to have the right conditions for life to arise. One of the major challenges in discussing fine-tuning and the multiverse is the lack of empirical evidence for other universes. While the idea of a multiverse is supported by certain theories, such as string theory and eternal inflation, there is currently no way to test or observe other universes directly. This has led some scientists to question the scientific validity of the multiverse hypothesis. As it may not be falsifiable, a key criterion for a theory to be considered scientific. The issue of fine-tuning also intersects with the concept of randomness in physics. The fundamental constants of nature could be the result of some form of random process, and their precise values could simply be a product of chance. If the universe began with a random set of initial conditions, it is conceivable that the universe we observe is simply one possible outcome among many. In this case, the apparent fine-tuning of the universe might not be as improbable as it seems, given the vast number of possible universes that could exist under different conditions. However, the nature of this randomness and how it applies to the laws of physics remains an open question. The implications of fine-tuning extend beyond the realm of theoretical physics and cosmology. If the universe is indeed fine-tuned for life, it raises important philosophical questions about purpose, design, and existence. Is the fact that life exists in such a finely tuned universe simply a coincidence? Or does it point to something deeper about the nature of reality? Could the universe have any other purpose beyond the emergence of life? These questions have been central to philosophical debates about the meaning of life, the role of humanity in the cosmos, and the existence of a higher power or purpose. As our understanding of the universe deepens, the mystery of fine-tuning continues to provoke fascinating discussions in both scientific and philosophical circles. Whether the fine-tuning of the universe is the result of chance, necessity, or design remains a topic of intense inquiry. Advances in cosmology, particularly in the study of the cosmic microwave background radiation, the behavior of dark energy, and the search for life beyond Earth, may eventually provide answers to some of these questions. For now, the fine-tuning of the universe remains one of the most compelling and mysterious aspects of the cosmos, offering insights into the very nature of existence and our place in the universe. The search for extraterrestrial life is one of the most exciting and profound scientific endeavors of the modern era. The question of whether life exists elsewhere in the universe has captivated human imagination for centuries, driven by the desire to understand our place in the cosmos and to explore the possibility of other forms of life. The quest to find life beyond Earth has been pursued through various means, ranging from the study of extreme environments on Earth to the detection of potentially habitable planets orbiting distant stars. While no definitive evidence of extraterrestrial life has been found to date, advances in technology and scientific understanding continue to bring us closer to answering this profound question. One of the key tools in the search for extraterrestrial life is the Drake equation, a probabilistic formula developed by American astrophysicist Frank Drake in 1961. The Drake equation attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy, the Milky Way. It considers several factors that influence the development of life, such as the rate of star formation, the fraction of stars with planets, the number of planets that could support life, and the lifespan of technologically advanced civilizations. The Drake equation provides a framework for understanding the factors that might contribute to the existence of extraterrestrial civilizations. However, it is important to note that many of the terms in the equation are uncertain, and estimates for their values can vary widely. For example, the fraction of stars with planets, FPFP, is now known to be quite high, thanks to the discovery of thousands of exoplanets by the Kepler Space Telescope. However, the likelihood of intelligent life emerging on a planet, the probability of that life developing technology, and the lifespan of a technologically advanced civilization remain largely speculative. This uncertainty means that the Drake equation does not provide a definitive answer, but rather offers a framework for thinking about the factors that influence the development of extraterrestrial civilizations. In recent years, the search for extraterrestrial life has been greatly enhanced by the discovery of exoplanets, planets that orbit stars outside our solar system. The Kepler Space Telescope, launched in 2009 by NASA, has played a pivotal role in this search by detecting thousands of exoplanets using the transit method. This method involves measuring the slight dimming of a star's light as a planet passes in front of it. By studying the frequency and characteristics of these transits, scientists can determine the size, composition, and orbital properties of exoplanets. Kepler's discoveries have significantly expanded our understanding of planetary systems, revealing that exoplanets are common throughout the galaxy, and that many of them are Earth-sized or similar in composition to Earth. Some of these exoplanets, such as those in the habitable zone of their stars, have the potential to support liquid water, which is considered one of the key ingredients for life as we know it. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on a planet's surface, not too hot and not too cold. Planets in this zone are considered the most promising candidates for the search for extraterrestrial life, as they may possess the necessary conditions for the development of life forms similar to those on Earth. However, despite the promising discoveries of potentially habitable exoplanets, the search for extraterrestrial life faces several significant challenges. One of the primary challenges is detecting microbial life as opposed to intelligent life. Microbial life, if it exists elsewhere in the universe, may be vastly different from life on Earth, and it could be difficult to detect using current technologies. In particular, microbes may leave behind subtle signatures in the atmosphere or on the surface of a planet, such as specific chemical compounds or isotopic ratios that could be difficult to distinguish from natural processes. For example, on Earth, certain microbes produce methane as a byproduct of metabolism, and methane has been detected in the atmospheres of some exoplanets. While methane could be a potential biosignature, it can also be produced by non-biological processes, such as volcanic activity. This makes it challenging to definitively identify microbial life from afar. Moreover, microbial life may not necessarily be confined to planets in the habitable zone. Extremophiles, organisms that thrive in extreme conditions on Earth, such as deep-sea hydrothermal vents or acidic hot springs, suggest that life could exist in a wider range of environments than previously thought. This has led scientists to consider the possibility of life in more extreme environments, such as the subsurface of icy moons like Europa, one of Jupiter's moons, or Enceladus, a moon of Saturn. These moons have subsurface oceans that may be in contact with rocky material, providing the conditions necessary for microbial life to emerge. The discovery of microbial life on such moons would have profound implications for our understanding of the potential for life elsewhere in the universe. The search for intelligent life, on the other hand, presents even greater challenges. While microbial life could be widespread in the universe, the emergence of intelligent life may be much rarer. The development of intelligence requires a number of factors, including the ability to manipulate the environment, develop complex communication systems, and create technologies. These capabilities are thought to be the result of millions or even billions of years of evolution, and they may depend on highly specific conditions that are unlikely to be replicated in other parts of the universe. As a result, the search for intelligent extraterrestrial civilizations is often focused on the detection of technosignatures, which are signs of advanced technology, such as radio signals, laser emissions, or even artificial structures. One of the most well-known efforts to detect extraterrestrial civilizations is the search for extraterrestrial intelligence, SETI, which began in the 1960s. SETI researchers use radio telescopes to scan the skies for radio signals or other electromagnetic emissions that could indicate the presence of an advanced civilization. The idea is that a technologically advanced civilization might broadcast signals intentionally or unintentionally that could be detected across vast distances. Despite decades of searching, SETI has not yet found any definitive evidence of extraterrestrial intelligence, but the search continues with more advanced telescopes and more sophisticated detection techniques. One of the key challenges in the search for intelligent life is the vast distances involved. Even if an extraterrestrial civilization is broadcasting signals, the time it takes for those signals to reach Earth could be tens or hundreds of years, or even longer, depending on the distance. Additionally, the signals could be faint or distorted by the intervening space, making them difficult to detect. The Fermi paradox highlights this issue, asking why, given the vast number of stars in the galaxy and the high probability of habitable planets, we have not yet encountered any signs of extraterrestrial civilizations. Several possible solutions to the Fermi paradox have been proposed, ranging from the idea that extraterrestrial civilizations are deliberately avoiding contact with us, to the possibility that they are simply too far away for us to detect. Despite these challenges, the search for extraterrestrial life continues to be a major focus of scientific research. The discovery of even microbial life elsewhere in the universe would have profound implications for our understanding of life and its origins. It would suggest that life is not a unique phenomenon confined to Earth, but is instead a natural outcome of the right conditions. The discovery of intelligent extraterrestrial civilizations, if it occurs, would be even more momentous, challenging our assumptions about life, technology, and the nature of intelligence. In the meantime, scientists are exploring a variety of other methods for detecting extraterrestrial life. One promising avenue is the study of biosignatures in the atmospheres of exoplanets. Instruments like the James Webb Space Telescope, which is scheduled for launch in the coming years, will be able to analyze the chemical composition of exoplanet atmospheres in unprecedented detail. By studying the spectral lines of light passing through a planet's atmosphere, scientists hope to detect signs of biological activity, such as oxygen, methane, and other gases that are associated with life. These observations could provide the first concrete evidence of life beyond Earth. As technology continues to advance, the search for extraterrestrial life will likely become an even more prominent part of scientific exploration. The discovery of life elsewhere in the universe, whether microbial or intelligent, would be one of the most profound achievements in the history of science, expanding our understanding of life, the universe, and our place within it. For now, the search continues, driven by the age-old question: are we alone in the universe? The universe, in its vastness, appears to be a tapestry woven from the very fabric of space-time. However, the nature of this fabric is not as simple as it might seem. While the macroscopic world of stars, planets, and galaxies operates under the laws of classical physics, the microscopic realm of particles and energy is governed by the strange and often counterintuitive principles of quantum mechanics. This quantum world holds the keys to some of the deepest mysteries of existence, from the structure of space-time itself to the origins of the universe. Understanding these quantum mysteries is not just a matter of uncovering the rules that govern the small-scale universe. It is also critical for understanding the large-scale cosmos and the very fabric of reality. At the heart of this quantum world lie concepts like quantum foam, virtual particles, and vacuum energy, ideas that have reshaped our understanding of space and time. These phenomena, though abstract, provide insights into the structure of space-time and how it behaves on the smallest scales. They also suggest that the universe is not a static or empty void, as it might appear to our senses, but rather a dynamic and fluctuating entity, even in its seemingly empty regions. These fluctuations, occurring at the quantum level, underpin much of the structure of the early universe and continue to influence its evolution today. Quantum foam is one of the most fascinating and perplexing concepts that arise from quantum mechanics. First proposed by physicist John Wheeler in the 1950s, quantum foam refers to the idea that space-time itself is not smooth and continuous as it appears at large scales, but rather a frothy and chaotic medium at the Planck scale, the smallest scale of space and time. At this minuscule scale, space and time are thought to fluctuate constantly due to quantum effects, and the very fabric of space-time is in a state of constant flux. These fluctuations occur at scales so small that they cannot be observed directly, but they have profound implications for the way the universe behaves at its most fundamental level. The concept of quantum foam challenges our classical intuition about the nature of space and time. In classical physics, space-time is often treated as a smooth, unchanging backdrop against which events unfold. However, in quantum mechanics, this view is no longer tenable. At the Planck scale, the effects of quantum mechanics become significant, and space-time is subject to fluctuations in its structure. These fluctuations can be thought of as bubbles or foamy regions of space-time that appear and disappear on incredibly short timescales. These quantum fluctuations are not just abstract mathematical concepts, but have real physical consequences, influencing the behavior of particles and energy in the early universe. In the context of the early universe, quantum foam may have played a crucial role in the formation of the universe's structure. During the inflationary epoch, which occurred just fractions of a second after the Big Bang, the universe underwent a rapid and dramatic expansion. This inflationary period stretched the fabric of spacetime exponentially, amplifying tiny quantum fluctuations in the fabric of spacetime into large-scale structures that would later become galaxies, stars, and other cosmic entities. These fluctuations, seeded by quantum foam, were essential in creating the cosmic structures we observe today. The idea that the structure of the universe on the largest scales may have been influenced by quantum effects. At the smallest scales is one of the most striking and profound insights of modern cosmology. The concept of virtual particles is another fundamental aspect of quantum mechanics that reveals the dynamic nature of spacetime. Virtual particles are fleeting particles that appear and disappear in empty space, governed by the uncertainty principle, which states that certain pairs of quantities, such as energy and time, cannot both be precisely measured at the same time. Virtual particles are not directly observable, as they exist only for an extremely brief moment, but they have measurable effects. They arise spontaneously from the vacuum and can influence the behavior of real particles and fields. Virtual particles are thought to be responsible for various phenomena, such as the Casimir effect, where two uncharged metal plates placed close together in a vacuum experience a small attractive force due to the presence of virtual particles. In the context of the early universe, virtual particles were an important component of the vacuum energy that permeated space during the inflationary epoch. During this period of rapid expansion, the energy of the vacuum was amplified and virtual particles were generated in abundance. These particles contributed to the inflationary process and helped drive the exponential expansion of the universe. While virtual particles are often considered to be a feature of the quantum vacuum, their effects are real and measurable, and they provide a window into the nature of spacetime on the smallest scales. Vacuum energy is another crucial concept in understanding the fabric of the universe. In classical physics, a vacuum is thought to be empty space, devoid of any matter or energy. However, quantum mechanics reveals that even in a vacuum, there is still energy present. This energy, known as vacuum energy, is a result of the constant quantum fluctuations occurring at the microscopic level. These fluctuations give rise to a background energy field that permeates all of space. Although vacuum energy is usually considered to be a form of zero-point energy, it has profound implications for the large-scale structure of the universe. Vacuum energy is thought to play a significant role in the accelerating expansion of the universe. In the 1990s, astronomers discovered that the expansion of the universe is not slowing down, as had been previously expected, but instead accelerating. This surprising discovery led to the hypothesis that a mysterious form of energy, now referred to as dark energy, is driving this acceleration. One possible explanation for dark energy is that it is a manifestation of the vacuum energy that permeates space. According to this idea, the vacuum energy density remains constant throughout space and time, exerting a repulsive force that accelerates the expansion of the universe. The study of vacuum energy and its connection to dark energy is one of the most active areas of research in cosmology. The properties of vacuum energy, particularly its role in the accelerating expansion of the universe, are still not fully understood. However, advances in quantum mechanics and general relativity may one day provide a more complete picture of how vacuum energy influences the universe's evolution. In particular, quantum field theory, which combines quantum mechanics and special relativity, provides a framework for understanding the behavior of fields and particles in the vacuum. This theory has been successful in explaining many phenomena, such as the interactions between electromagnetic fields and particles, and it may also offer insights into the behavior of vacuum energy on cosmological scales. The study of quantum mechanics and its implications for the universe's fabric also intersects with the search for a theory of quantum gravity, a theory that can unite the principles of quantum mechanics with the framework of general relativity. General relativity, formulated by Albert Einstein in 1915, provides a description of gravity as the curvature of space-time caused by mass and energy. While general relativity has been highly successful in describing large-scale cosmic phenomena, such as the behavior of stars, galaxies, and black holes, it does not account for the effects of quantum mechanics, which govern the behavior of particles at the smallest scales. A theory of quantum gravity seeks to bridge this gap by describing how gravity operates on the quantum level. Several candidate theories have been proposed, including string theory and loop quantum gravity. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings that can exist in multiple dimensions. These extra dimensions could provide the key to understanding how gravity fits into the quantum framework. Loop quantum gravity, on the other hand, proposes that space-time itself is quantized, consisting of discrete chunks rather than being continuous. Both of these theories are still in development, and much work remains to be done before a complete theory of quantum gravity can be formulated. Understanding quantum mechanics and the fabric of the universe also has implications for our understanding of the early universe. The conditions present during the first few moments after the Big Bang were so extreme that classical physics breaks down, and the effects of quantum mechanics become dominant. The universe began as a hot, dense, and nearly uniform state, with all of its mass and energy concentrated in a tiny volume. As the universe expanded and cooled, quantum fluctuations in the fabric of space-time were stretched to larger scales, providing the seeds for the formation of galaxies and other cosmic structures. These quantum fluctuations were amplified during the inflationary period, which occurred just fractions of a second after the Big Bang. Inflation explains many of the observed features of the universe, such as its uniformity and large-scale structure. But the underlying quantum processes that drove inflation are still not fully understood. Advances in quantum mechanics and cosmology continue to shed light on these mysteries. Experiments and observations, such as those conducted by the Large Hadron Collider, LHC, and the Planck satellite, are providing new insights into the behavior of particles and fields in extreme environments. In particular, the study of the cosmic microwave background radiation, which provides a snapshot of the universe just 380,000 years after the Big Bang, has revealed subtle imprints of quantum fluctuations from the earliest moments of the universe's existence. The quantum mysteries of the universe are vast and complex, and while much progress has been made, many questions remain unanswered. Understanding these mysteries is crucial, not only for our understanding of the origins and evolution of the universe, but also for uncovering the fundamental nature of reality itself. As we continue to explore the quantum realm, we may one day unlock the deepest secrets of existence, secrets that could transform our understanding of space, time, and the cosmos. We'd love to hear your thoughts in the comments below. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.